Hi to everyone. Thanks for joining us. I see that the participants are joining slowly but surely, so that's a very good sign. Again, thanks for taking the time to join us today. We'll wait another 2-3 minutes and then we will move on because as you know, when we have to deal with virtual workshops, we need to get organized a little bit differently. So we decided to have short talks. I see that Aki already has 200 slides, so I will have to manage. And we expect mostly to have time for questions and debate. So as you know, this is a webinar system, so I'm sure that you get used to it since that we are now locked down for almost, we have been locked down for almost a year. So you can interact through the chat, but questions, please. We will invite you to ask your questions through the question menu. And those questions will be handled by the chairperson, who will be in charge to select the questions and then, of course, direct them to the speakers. And please feel free, of course, to interact as much as possible, because this is really the objective of the workshop. So let us start formally. So it gives me great pleasure to extend to you all a very warm welcome to this first online workshop on slices. So slices for many of you make sense, but sometimes, you know, it's difficult to match a meaningful acronym. So slices stands for Scientific Large-Scale Infrastructure for Computing, Communication, Experimental Studies. But what it means is that slices ambitions to deploy a scientific instrument to support evidence-based research in digital infrastructures. So slices is really a community effort. This has been developed in Europe, but this is also fully embedded and articulated with an ambitious international effort, as we will see today in the first session after John's keynote. So in a time calling for clear support from science, the COVID-19 episode has demonstrated the difficulty for the scientific community to dialogue with the policymakers and the citizen. I hope you share this observation. And more particularly, it reminds us that providing evidence is a very difficult task that is based on a formal methodology, often grounded on experimental research, and that this process is long and complex. So for that purpose, as far as we target to deploy a scientific instrument, we are challenged on what are fundamental scientific questions. So what is the demand? And this is not about demonstrating the existence of the Higgs boson, but rather to support the design assumptions of really complex physical and virtual systems. So I will maybe here just quote Nick McQuon, who you all know. And he gave a talk lately with two very interesting observations. First is, we will think of a network as a programmable platform. And this echoes to what we have tried to develop in the past with respect to the design of test platforms. And the second quote, which is a bit provocative, we will no longer think in terms of protocols, but instead we will think in terms of software. And that's a very important comment with respect to the direction that we are taking now on board of the design of these digital infrastructures. So we'll have two sessions tomorrow dealing with the demand. So one from academia and the other one from industry. Of course, this is a snapshot. And for sure, you can certainly find here and there different roadmaps regarding beyond 5G, 6G, and the evolution of HPC and cloud and so on and so forth. But those will be the opportunity to debate about those scientific questions and how we can formulate those scientific questions. So designing a scientific instrument also questions our ability as a research community to align with the best practices used in other fields. So including, for instance, open research data, fair access, and there are obvious links with the EOSC initiative here in Europe. And we'll welcome a closing session from the DG Connect on this topic tomorrow. So on the positive side, everything is positive, but even on the more positive side, we should have a competitive advantage, as digital infrastructures are the foundation for the digital transformation of our societies, as it is perceived today, for instance, with respect to 5G and eventually moving towards 6G technologies. So as I said, because this is a virtual event, we have invited speakers to be quite short so that we leave time for discussion. And we have organized the workshop in 2 half days so that you can breathe a little bit. So the first half day, this afternoon, will be mostly dedicated to a keynote. And I will then shortly hand over to Andrea and John. And then we'll have an international fora. And we're very happy because despite of the time differences, we have both Aki from Japan and Manu from the US and Bernard and David from Brussels and Paris. And I would like to thank them all, of course. And the talks will be, or the full workshop will be recorded. So it will be available online later on our slices-ri.eu website, as well as we'll have access, of course, to all the presentation. And I would like to thank the European Commission, DG Research and Innovation, and especially OPO, Lorenza Saraco, for permanent support. Of course, gratitude to all speakers. I know those are busy and stressing times, but thanks for taking the opportunity to join us for the 2 days. And of course, gratitude to the organizers for the diligent work, so namely Stavula, who is our master of ceremony, together with Frédéric and Emily for their continuous valuable support. So I'm going to close now by wishing you and wishing us a stimulating workshop. Please keep interacting through the questions and the chat. Thanks for your attention. And now I'm going to hand over to Andrea. Andrea, the floor is yours, introducing the keynote.
Okay. Hello, good afternoon, everyone. Thanks a lot, Serge, for the introduction, and thanks for organizing this nice event. It's really my pleasure to introduce our keynote speaker, Professor John Crocroft from the University of Cambridge. I mean, we all know John very well. He's one of the most visionary researchers in our community, widely recognized in Europe and worldwide. And he is a source of inspiration for many young researchers, including me when I was a young postdoc in his group. So John, he has many roles and achievements. He's a Marconi Professor of Communication Systems at the Computer Lab. He is a fellow of the Turing Institute, an honorary professor in statistics at in the University College London, and is a member of the Royal Society, ACM, British Computer Society, the Royal Academy of Engineering, and IEEE. He is also a member of many technical advisory boards in the industrial sector, including Fazira, Matrix, AdDex, CognitionX, Ensemble, etc. And IMDEA Network is also a partner of our initiative. So it's really important, I think, for us to have a keynote from John, because we need inspiration in order to design the platform that Serge was talking about. So John, thanks again for accepting our invitation and being our keynote speaker. The stage is yours. Any questions you have for John, please put them in the questions tab, because the chat is going to be a little bit busy. So put questions for the speakers in the questions tab so that the chairs will be able to ask the questions to the speaker. So John, please, the stage is yours.
Hey, thank you. Do you hear me okay? Okay, great. I never can tell. I haven't used this platform before. So yeah, it's a kind of an interesting experience that we can all relate over the last year or so, which is learning a new video conferencing platform approximately once every day, and somebody proposes using some other tool you haven't tried before. I guess the WebRTC integration has meant it's very easy for new entrants, which is a really interesting example of a platform for innovation. And this looks like a pretty good platform, actually. So the browser integration has certainly meant that you don't have to write the video codec and the audio codec the way we used to have to in the old days. And if you think about, the first thing that people came across probably in the wide public was something like Skype in its original version, which was very, very sophisticated in terms of being fully distributed and had pretty good audio and video codecs in it from very early on, as well as some interesting economic business models. So it's a really, really innovative, which then got bought by eBay. And then Microsoft then rapidly became less innovative, which was a shame. But now we have all these other platforms, so that's pretty interesting. So so I'm going to talk a bit about a kind of wide-ranging talk. So I wasn't quite sure what kind of talk you wanted. And I'm just going to check my slides actually go backwards and forwards, because that's, yeah, they do great. So I'm only got asked recently to do this talk. That's fine. I'm sitting here at home, vaccinated, by the way, so I could go out and be safe. But of course, we still worry about other people might not be safe from me. And working from home, teaching from home, doing research from home. Where do I do teaching and research? And Andrea actually mentioned that I actually have two different places I normally work. And one is Cambridge University in the computer lab, and the other is the Turing Institute, which is the UK's National Institute for AI and Data Science. And I've been working there 50% of the time since it started. So that's actually 5 years now. And some of what I'm going to talk about is the experiences that we've had there, because it's a collaboration, although it's only UK wide, it's a collaboration with 13 universities and 5 or 6 strategic partners. And the strategic partners are large organizations like the UK government or Intel, Microsoft, HSBC, which is a large bank. The National Health Service in the UK is another very large collaborator. And we do AI and data science with all of those organizations. And we do basic research, but we actually have to apply it with those partners. And so we're doing large scale, distributed, networked, privacy preserving machine learning across these all these organizations. And my original role in the Turing was from the system side, was to say, well, what kind of systems do we have to build or assemble or deploy or connect to enable those activities? And that, that in a way, I guess that resembles some of the things that one would consider for for infrastructure, for research, where the research is networked. And of course, inherently, almost everything is networked now. But the scale of the problems is pretty huge. In fact, the latest program at the Turing is our AI for Science program. We originally didn't have much of the AI work being applied to physics, chemistry, biology, apart from medical systems, but now we have the physicists on board, and those people have really crazy amounts of data and really large scale problems, and high data rates as well. Of course, there are large problems in AI like protein folding, which come out of cell biology and so on, which is super interesting as well. But so what I'm going to talk about though is kind of 3 aspects of what we faced in our work in the Turing, but in Cambridge as well, where we tackle some of the problems. But most of the work in Cambridge is in the lower level. My work anyway, my research group is in lower level systems. Practically tackling the next generation of technology that might work to solve the problem. The work in the Turing from a systems and networking perspective has been in the application of kind of state-of-the-art ideas for application domains, so for essentially customers who themselves have their own research, but it's in their domain. So it would be health research or financial service research or government data science and so on. So the three areas I want to kind of talk about that we've had to tackle And I'll kind of do a deep dive in one particular piece of this, which I think is an interesting technical challenge for research infrastructures and any infrastructure for distributed systems today. But the three areas of federation, how you generalize from research that you do, and then the problem of heterogeneity. And I'll explain what each of those three areas is as I go along. The deep dive specifically is just an area that I think is very interesting right now, which is the kind of hot topic for several years now has been this whole edge processing and fully decentralized systems. And we actually have some pretty impressive large-scale deployments of decentralized systems recently. I would say, for example, most countries that deployed a COVID pandemic contact tracing app used a Google Apple exposure notification system, which is a decentralized system. And the UK, for example, we have over 20 million people download and use that. And it's demonstrably actually helps reduce the cases in the UK. Unfortunately, the government made other mistakes, which didn't help, but at least that component did help. But that's a large-scale case of a decentralized system. And there are other interesting decentralized systems. For example, in digital government and identity systems in Estonia, they use a very decentralized approach. The citizens own their own data, and it's very interesting. The other area that's put a part of this is where some of this edge processing is just inside the network. And sometimes that's just taking advantage of the programmability of devices in the network, and we heard about that from Serge earlier. The network is increasingly programmable because the switches are maybe P4 programmable and so on. And that programming doesn't just have to be for networking; it can be to assist applications, and maybe things like transcoding media or crypto or other things you might want to do just inside the network and not right at the very edge. Some people in the telecom world, and particularly in the cellular telephone world, they call that edge computing, even though it's just inside the network, one hop in from the end user. And that's but that in-network compute is super interesting as well, and it's sort of part of the federation problem. So the first area, federation, I want to talk a bit about, and I think what we learned here is there are two very different scales of federation. So one example of federation of processing is where we, in the UK, we've been taking healthcare data from hospital wards, from general practices, and processing that to understand the pandemic, for example. It's just one area. There are many other things. One example of processing was to take real-time dashboard data from intensive care units and take the doctor's actual treatments they were using and do adaptive trials of the treatments. And adaptive trials is a hot topic in medicine, where instead of just taking groups as A/B testing, you actually vary all the parameters for all the users, and you learn things very, very fast, and you have to change everyone's behavior towards the better treatments, the more successful outcomes, super fast. Otherwise, you end up in a very bad ethical place, but you end up in a better place because you end up with very complex, high-dimensional treatments where there are many different parameters. You end up with a very interesting result. But the federation in that case is not particularly large scale. The examples we're looking at were probably on the order of less than 100 hospitals, less than 100 ICU intensive care units. So but the reason for federating the processing is you don't want to move the data around for privacy reasons. It's medical data. So you do local models, you build local models, and you share model parameters, and then you build up more accurate models, and then you give the medics back the outcome of the models, which they can compare with the data they have locally and adjust their treatment. So that has all the right properties in who's allowed to see what data when, and does not involve moving specific re-identifiable patient record data around. That kind of federated processing, of course, there are people, if you're interested in the privacy problems of federated processing, probably the best person I know in the UK is Emiliano De Cristofaro at UCL, who's a professor of security there, who's done some very good work in showing there are limits to the privacy you can achieve there. So that kind of federated processing is used with caution. It's interesting. But the other area of federation, I think, is where 5G and 6G networks are coming in, and the kind of promise of the capacity and coverage with these networks was for very large numbers of devices with low latency. But even with the low latency, you still want to keep processing local. So if you have a large number of smart cars, smart vehicles, smart houses, smart healthcare monitoring on your person, and so on. You have extremely large numbers of devices, and the Federation now has to operate at a scale of billions or trillions. And I think here the problem is the coordination problem. It's the scale problem that you face. So, for example, what we're used to doing with processing, whether it's public cloud or private cloud, in whether you federate or not, is we have some coordination tools, and typically, the most common widely used tool would be something like Kubernetes. So we were looking at bottlenecks in Kubernetes recently for federating a number of edge devices, monitoring and controlling what's happening in smart homes, and it has some severe bottlenecks because basically, if you get down to the details, that its Secretary uses RAF-style consensus algorithm to deal with replicas, and this is a common problem that may have bottlenecks. And when you federate very large numbers of edge devices and you have variable capacity and throughput, and latency and availability, then these consensus algorithms really better work. And if it's a consensus algorithm, the data itself of the end application, that's one thing. If it's a consensus algorithm for a replicated control system or coordination system, then you don't have anything working, whether consistent or not. And so that's actually a real challenge to scale that up. And there are interesting challenges in how to tackle the problem, both from improving the consistency schemes in terms of scalability of dealing with heterogeneity. I had a student, Heidi Howard, who worked on this, and some other folks in Cambridge who have done some work on that, people at VMware, some very cool work. The other is you can also relax the consistency requirement. It depends really what your end goal is, and it may be possible to choose a kind of eventual consistency models and so on. So that's just one example of a coordination problem at a very large scale. So while deploying a large number of instances in the cloud and coordinating them to start a deployment for long-lived large-scale computation, something like Kubernetes is a pretty good tool. For a really, really large scale with lots of edge devices, this may not be so good. And of course, and when you're looking at the task that's being done, I've mentioned application tasks, which are sort of facing an end user, but of course the network operator is equally interested in this. So one example would be building models of faults, and there have been papers in the last couple of years where the root cause analysis of what's gone wrong in a cellular network has been carried out doing some federated learning, but the data is pretty large scale. You're looking at all the cell towers, and particularly if we're looking at the microcell deployments of maybe 6G, there could be, again, many millions of those per country, and the fault rates are fairly high. I was surprised when I read the paper I'm thinking of, which I can't remember who the authors were, and I think it was from China. The fault rates were on the order of 1 million faults a day per city, where a city would be, Paris or Berlin or London or whatever. And of course, these aren't necessarily permanent faults, but they're things that ring alarms, and you need to learn it. Are they significant or not? So you have to do some kind of pattern recognition and machine learning and so on. So facing into the network is a requirement, because there's no way humans are going to look at those faults and diagnose the problem without at least some dimensionality reduction somehow, and that's going to require some learning, and you can't move the data around if you've got faults. So you want to learn the local model, and when things recover, then maybe you share the model parameters and so on. So this is another super interesting area, I think, where federation is going to be fairly essential. So I've mentioned some of this, as I've been talking. So looking ahead, I think there's arguments for federation which have been made, and for edge processing or near edge, just inside the network, have been made that potentially you use less network capacity in moving data around. Instead of moving data around, you move model parameters or summarizations. So that reduces the energy cost, which means your system is more sustainable. And from my perspective, moving all the surveillance data around to a large data center and then analyzing to see how many cats you can see in the images is a complete waste of energy. It's not quite as bad as Bitcoin, but it's heading that way, and it's unacceptable in the climate emergency we live in. So there's a plus point in this argument. Also, of course, if you do a decentralized system for building models, it's potentially more resilient. Instead of moving all the data to one center, which might fail, or access to it might fail because of some major incident, you have lots of independent sites with much higher resilience. But all of that is true. But for a given site, a given endpoint, the availability is lower because we don't engineer end users' access to be as available as we do. We put a lot of heavy engineering into data centers, network access, and highly fault tolerant. In fact, when I look at Cambridge University, we have a couple of data centers, and we have, I think, 5-fold redundancy in our network access now. And for years, it's been triple redundant. And that's quite expensive because it's I think it's up to 100 gigabits wide area access now. So so availability in a decentralized system, a federated system, may be more complex. Now, of course, one of the interesting things, there's a really nice paper by a whole bunch of people that came out towards the end of last year. I think it was an IMC, but Smaragdakis and Anya Feldman, usual suspects, wrote this really nice paper about how the internet had changed during the pandemic, with very large numbers of people working from home. And actually, some of the re-engineering that ISPs did increase availability significantly, as well as flipping around the typical bandwidth allocations because of the asymmetry of typical home access. And the major success story there. So, the last 3 or 4 decades of internet research and development, and can make major claims about being a benefit to society, but we need to go further. And clearly, more optical access from home is an improvement because there's less failure modes than electrical, but also multiple resilient access from home, where you have multiple paths. And in my house where I'm sitting right now, I can go via my neighbor's Wi-Fi. We have an agreement, although they put me in a lower priority than their home traffic, but that means I actually have 4-fold redundant access from my home. And that's ignoring that I could pick up my phone and tether this talk via my phone, and it would be on 4G, I think, where I'm sitting at the moment. So that's pretty good, but we could do better. But in the absence of that availability, of course, we can use fault-tolerant algorithms and fault-tolerant data. And so that's an interesting space, because I think that the climate emergency is going to demand we reduce the energy costs. And data centers they're fine if you have inherently centralized data. Data that was gathered centrally, and perhaps it's part of government. It could be some parts of healthcare data, and long-term data about that. But there's an awful lot of real-time telemetry about the world, and local processing of that and sharing models seems much better. My canonical example of this is smart meters for utilities, where smart meters send data in UK, I think it's every 90 seconds, to the utility company, and they build a model of all the different homes. But in fact, there are only about 100 different kinds of homes using electricity and gas and water. There's 100 different kinds of, so there's a list of parameters of the busy hour, the busy day, the busy week of the year, and so on. And you really just need the values and the histogram for the distribution. You really don't need all the data every 90 seconds from the UK's not 35 million homes. So learning the model in the smart meter and sending the model parameter around is both more energy efficient and privacy preserving to a large extent. Of course, if you want to scale up that federated learning, you probably need to build some kind of self-configuring hierarchy. That's super interesting. In fact, going back, I mentioned video conferencing, Skype was extremely clever in that it auto-configured nodes, that it measured very high bandwidth and connectivity and symmetric bandwidth, and it turned those into the coordination points for end users, and it could also turn them into transcoders or other things if you wanted to go that way. And I think that kind of self-organizing around the variation of capacity and resources at each point in a distributed network system is something we need to go back and rebuild at scale. And there always will be this variation. I had ADSL to my house for 20 years, and then along comes having to teach from home with video, and I had to go and get fiber to the home. So now I have 100 megabits, so and it's always on, and I've got V6 addresses from my ISP, so I could serve as a supernode in the old Skype model quite easily without impacting my own use significantly. So that, but that needs to scale up and and also take account of business models. As I mentioned, this sort of federated models don't automatically guarantee privacy. You may still need to worry about certain aspects of even models. Models that are sufficiently complex can reveal some of their training data, but also as you build a model in a local node, you still need all the nodes to actually implement privacy in the right way, and that may need some kind of enclave technology or other techniques, which are fairly well known. But I think we need to improve the privacy technologies sort of ongoing fight. We also need to understand the privacy models offered by distributed processing of private data, and explain it to people, including lawyers, so that the law reflects what things can and can't do. So if I manage my keys properly, I can do somewhat homomorphic encryption on data in another country, but currently that would not be legal under GDPR. But actually, in practice, it's where the keys are, not where the data is, that matter. So the law could be modified to account for things like that. And there are other examples we could go through. Okay, so oh, you're going to have to excuse my photographs, actually. Sorry, that photograph of the Federation, you may not be able to see it very well, but that actually is my family have joint citizenship of Ireland and the UK. And so that shows that an Irish passport slightly outweighs the UK passport because it allows you to live in the UK, but also go all around the EU. So I'm just putting my EU credentials down there. Sorry, that was just a visual joke about Federation. So, okay. The second topic I wanted to look at is heterogeneity, and this is really a big hot topic right now. And we hit this in both in the AI machine learning world, but also in networking, obviously. And this has been around, but it's just getting, I was going to say worse, but it's not worse really. It's more interesting, and there are good reasons for this. So heterogeneity, and I've used the word speciation. CPU speciation, by which I mean the increase in the number of kinds of species. And I'm making a reference here to evolution. So one of the models of evolution in the ecosystem of animals and plants is there's a thing called punctuated equilibrium. So everything stays roughly the same until there's a change to the environment. And then the change in the environment seems to cause a higher rate of development of species. And then that, after a period of there being many different kinds of creatures around, there's a selection process that's always happening that brings it back down to a smaller number of species. So if you look at those of you old enough will remember back in the 60s and 70s that there were very large numbers of computers with completely different processors. In fact, I was talking to somebody recently about programming an ICL 1900 and a DEC 10, and the ICL 1900 had a 24-bit word and the DEC 10 had a 36-bit word. And I was porting code from one to the other, and the code actually was a convolutional random number generator. So it really mattered that it was exactly right. And of course, then we went through PDP-11s and so on. It was 16-bit, and then suddenly there was a VAX, and it was 32-bit, and then there were Intel processors and 32-bit, and then 64-bit, and then there were ARM processors. But that's so that settled down, and we just had to worry mostly about Intel and ARM. And then along comes Apple and builds its own processor, and what used to be the Sun Spark processor, and Oracle still use. But now we have much faster speciation because we have accelerators. And originally these were narrowly focused on things like gaming and also render farms from CGI for special effects in movies. But of course, GPUs, sort of large numbers of tiny cores, turn out to be really useful for other things like machine learning. And then people realized they weren't necessarily the most efficient way to do that. And so they've targeted particular problems, famously Google's TensorFlow TPU, which is essentially a tensor operation accelerator. GraphCore is something from the UK, which some of you might know about. And of course, at networking, we have a similar thing where my colleague Andrew Moore works with the folks at Stanford on the net FPGA. So FPGA is a pretty radical departure from most people's programming experience. And of course, people have built custom silicon for data centers for RDMA and other tricks they use, and so on. And so if you're building networks and you're doing any in-network processing or offloading or all the other things we've looked at for decades, you don't have to worry about this very widespread range of different systems you have to program that have very different performance characteristics and suitable for different problems. And I'm in awe of my colleagues who managed, my friends who managed to put Paxos onto P4 switches. I mean, that's incredible. Building one of the world's most complex consensus algorithms onto P4. That was pretty clever. But that's just one of many things you might want to put into very baroque systems, very very strange systems. And we're not just talking about acceleration that's targeting machine learning, because the acceleration targeting networking itself could be used for accelerating machine learning. In fact, Microsoft certainly have used their hardware for NICs that they use for RDMA. They've retargeted that for machine learning. So it goes both directions. So that heterogeneity is something to grasp, and it's very tricky because it's not something you can hide with a compiler. The trendy thing would be you write all your secure network code in Rust, but there might not be a Rust compiler onto these things. And then you might be clever and you write a backend for the Rust onto, say, P4, but that might not implement optimizations that might be possible for some other hardware target. So this is, a whole other area where, like we heard from Serge, software meets the networking, software meets distributed systems, software meets machine learning, and all these things put together. But now it meets this wide range of hardware, and you don't have to worry about things that we didn't worry about for the last 20 years because we just had compilers that compile pretty well onto Intel and onto ARM processors. But now suddenly you've got these rather strange things, and they're not just different word lengths. They support all kinds of different parallelism, all kinds of specialized data structures, which are really quite different. And so the range of systems we have to cope with and heterogeneity has just grown, and incorporating acceleration as accelerators has consequences potentially for energy use, potentially for privacy, potentially for resilience. We're going to hit more bugs because these are completely new vertical stacks that are running on these things. And you have this, like I said, on the federation topic, you have these problems that are often dealt with by modern statistics. Machine learning is just modern statistics, which could be facing the CPU or facing the network. There could be things you're trying to solve that are learning the faults in the network, learning patterns, anomaly detectors, and so on. Or it could be an application, an end user's domain is running something, and you can move code in either direction for those two user communities. So there's an actually interesting scaling problem here as well, because now you have this heterogeneous platform, and your coordination tools have to be aware of that heterogeneity. So clearly, this is something, if you buy resources in the cloud, then or you rent resources in the cloud, typically you say, I need this many virtual CPUs, but I need some GPUs because I'm doing some natural language processing. But now suddenly you might have many more choices, and making that decision is one of these multi-dimensional optimization problems, which are hard. So that's a heterogeneous problem space. And then I'm going to talk about something very different for the last, well, I've got 5 minutes, I think. I think what 5 minutes before Q&A.
Well, actually, you have a bit more time, John. Don't worry. We have so take your time.
Okay. Okay. So, well, one of the things I think about building research infrastructures is that the really big tasks are associated with people, not with the technology. So we have had a number of research infrastructures for networks and distributed systems that have been pretty successful over the last 40 years. And the internet was a research infrastructure originally. So certainly when I started working on things in 1980, and I was hired as a researcher for programming a measurement system, which was distributed. It ran on the satellite Atlantic Packet Satellite Network, which had uplinks from what's now CNR, I guess, but it was Keynote, had a satellite group, really famous bunch of people. And then there were links in NDRE in Oslo. There's one in Germany and one in London, and one in the east coast of the US. And we built a distributed measurement system for that network because people were interested in how well it worked as one of the hops geostationary satellite, Intelsat 4, and there were all these Earth stations, and then there were satellite IMPs, and they were connected to IP routers. And in fact, 1980 is when we switched from the earlier internet protocol NCP to TCP/IP. And so I built this measurement system that essentially attempted to synchronize packet logs so you could compare what was happening. And some years later, about 88, 87, 88, we were measuring TCP performance over it. And Van Jacobson proposed this new TCP congestion control. And he was super interested because we were on this link that was only 64 kilobits a second, but was on a geostationary satellite path, which was a 0.72 second round trip time. 0.7 seconds is a very, very long round trip time. Only very recently have we exceeded that with the successful Mars landing, where the round trip time is minutes. So when Mars is in opposition, you're in, I think, roughly 14 minutes. And even when it's the same side of the sun as us, it's still a few minutes. But anyway, even back then we had 0.7 seconds. And the interesting question was, how well would the RTT estimator combined with the slow start and congestion control work on a path that included a link like that. And so, that was useful to have as part of the infrastructure to learn how that would work. Unfortunately, when we turned off the satellite links in, I guess, the late 80s, people forgot about that. And more recently, when people have been providing rural broadband using satellites, they have discovered that TCP doesn't work so well because it didn't include some of the things we did back then, which is a real shame. And some of the things were cross-layer. There was cross-layer optimization on that network because we knew, working with the satellite people, we knew what the error characteristics were. So we decided, perhaps we should use forward error correction in the link because that will mask those errors. And so TCP won't see wireless loss as congestion. And this is a problem, in cellular links, you get wireless loss and it's seen as congestion. And there's been a thing that people that do TCP level work in networks have tried to tackle again and again, and it was kind of, well, actually we knew about that a long time ago. But anyway, but the point is that that story, which is an ancient piece of history, says that you need people that remember stuff or write it down so that you have that knowledge captured with the technology. And one of my favorite examples of this was, I was reminded very recently by somebody at the Turing Institute who was doing some networking, and they just noticed that my name was acknowledged in Rich Stevens' TCP/IP Illustrated book, because I was working with the editors back then. And that book, the first two volumes anyway, and the new edition Kevin Fall's done, it's a fantastic book because it captures a huge amount of knowledge. It's an annotated BSD kernel source code of the TCP stack and a walkthrough of the protocols operating the packet capture with a commentary by Rich Stevens, which is just beautiful. So, it sort of almost should be required reading for anyone starting a PhD in networking, even though it was a little bit out of date until the new edition. That repository of knowledge is extremely valuable, and the knowledge includes this source code. So the first volume is the walkthrough of the protocols operating and packet capture, TCP dump, essentially. Somewhat out of date, but the methodology is fantastic. And the second book is the walkthrough of real code, which, admittedly, there are probably many more Linux systems and BSD systems these days, but it still gives you a bunch of very elegant implementation tricks. It's kernel code and it's in C, perhaps not the best example to start from in software today. Most of my students these days do projects in Rust or OCaml. Those would be our choices. I'm sure the French people here will appreciate the OCaml use, which is a lovely language, and Rust is also a nice language. But the point here is that you need to keep this information around and not forget it, and keep referencing it, so that when people bring up a thing that's not a new problem, you say, well, actually, there's some earlier solutions. So that's this repositories that I think are really essential. So when you build a network infrastructure for research, you need to build repositories where you keep all this information. Could be, and as we did in not just early internet work with the what we called IENs, which are Internet Experimental Notes, which are precursors to RFCs, but also in Planet Lab, where that people had a very standard way of keeping notes that they had, experiments they'd run on Planet Lab. And when they built a piece of commonly usable infrastructure, for example, a measurement tool that would just do a kind of ping mesh type thing, then that would be shared. So the next paper somebody was writing could just use that again, or use the results of it. So it could just be a useful collection of telescope data that said this is what the internet looks like if you want to build an application that runs in that kind of infrastructure. And we've just been building with a colleague from Oxford. Shock horror, Cambridge works with Oxford. Yes, we do. A guy called Ed Orton, who we've been building a digital twin of the cellular infrastructure in the UK. So we know where all the cell towers are, and we know what the spectrum allocation is to the different providers. And so we built a model that just captures all of that. So if you want to figure out what happens if demand changes, then you can use that model to do that. We actually did another model, which was to improve the map of Wi-Fi APs. It turns out a lot of people do war driving, but they don't allow for some statistical correlated errors in how they do that. So there's another paper coming out on that. And that kind of thing is, you know, it's an infrastructure in itself, is that knowledge about what's happening. And then the second point on this slide is repro, as in reproduction, reproducible work. And I really, you know, I can't stress enough how important it is that work is reproducible. That any experiments done are presented in such a way that somebody else can rerun the experiment. They don't have to get exactly the same result, but they need to be able to explain why there's a difference. And I think this is increasingly, I'm very happy to see that a lot of the top conferences now have artifacts. You know, you can attach to your paper a data set or code or both, and then there's typically a subcommittee that will evaluate the artifacts, and often the best paper prizes either only allow for people that actually have the artifact, or there's an extra prize for somebody doing that, if it's done really well. And that's, that okay, people say that's going to slow things down. It's going to take you longer to get the paper out the door. That's good, because that means we have less papers to read, and the papers we do read are better. There's no problem there being less papers. I know somebody will say, oh, what about promotion? But if everyone does this because you have to, then the quality bar will be higher, and that will be good. So I think reproducibility is massively important. When you're building an infrastructure, obviously you want to build alongside it the measurement systems, but also the ways you capture what you're building in software, in configuration, in its performance at any stage, the set of things that other people are doing, and any unexplained artifacts, things that don't behave exactly the same way. They can be left as interesting challenges for people to look at. We're always looking for problems for master students or first year PhD students to tackle, where they may not be all completely embarked on their PhD. So there's a nice problem where there's this unexplained problem. Or here's an experiment, looks interesting, but we want to reproduce that, and can we try that? And increasingly, that's a valid piece of work to do. And then long-term curation of any output, I think, is really important. Like I say, you'd really like to not have this sort of forgetting function where something that actually turned out to come around the curve and be relevant again has disappeared off everyone's memory, and that I don't have a great answer on how to do that. Actually, I think that's very tricky. It's difficult to motivate people. We really, there's not a PhD or first year or master student task. But I think there may be. It's not something that's easy to incentivize how you do the long-term curation. There have been some examples. I think the repository of mobile and wireless measurement, Crawdad, it was done by folks Dave Coates and Tristan Henderson at Dartmouth College. I think Crawdad is a really, really good example. They curate data a long time, and they index it properly. They tell you how to cite it. They do all those things. So there are positive examples. And then there are other things about which may help. And this is something I've become a bit of a fan about, which came out of the work that people in the Turing do, and I'm sure other people do, but I had not encountered this before. So almost all our research groups, I can't spell Jupyter, that's been auto-corrected, but you probably know what I mean by Jupyter notebooks. Almost all our research groups, when they start a project, they set up a Jupyter notebook for the project, and they do these processes, continuous integration processes. And this is mind-bogglingly useful, because when somebody new arrives, you can onboard them, you can bring them on stream in the project, and they can just read through this thing and it will have the code and the explanations, any data, and so on. And it's just, there are other tools, but this is one we commonly use. And that just lends itself to improving explainability and reproducibility. And, it is a repository. It's a repository of code and data with design documents. And you can feed it into digital twin design if that's, that's something you want to do. You can also potentially use it to record the negative outcomes. Some of you have probably seen the very cool work by Mark Handley from UCL, who's done a bunch of very cool projects over the last 20 years. But his most recent project was his youngest kid has built a hydroplane, a radio-controlled hydrofoil boat. And there's a video on YouTube of this, which they published very proudly. It's entirely the kid, who's I think 11 years old, and they 3D printed a boat, but in the process, they recorded all the steps and they chose different propellers and different float sizes and different power motors and so on. And they recorded the failures. One time this boat is doing 80 kilometers an hour. I'm not kidding. This kid has built this beautiful thing. You can look for it on YouTube. And it just broke into pieces because they hadn't built it strong enough. And they recorded the negative outcome in the talk. They said, they discovered the power weight ratio, doesn't work and it doesn't get the front out of the water enough and so on. So that record is super interesting because it acts as a lesson for future people who want to build, 3D print a hydrofoil, why not? And you can see, don't do this, right? It's really useful. Then obviously, curating things, as I mentioned, is like, how do you prevent website decay or disappearance? Indeed, I was just trying to find some early version of a web page for somebody, and I realized that the thing I was looking for predated the Wayback Engine. So even if you look at Wayback, it goes back and finds stuff back to 89 or something. I'm not sure exactly when it started, but it's it didn't have snapshots from before this point. 99. Anyway, and then the other thing, of course, is in this process, continuous integration process, you can also document things like applicability. You've developed some new algorithm. You could say this is applicable in these. And by the way, future you might want to test and see if you can reproduce these results in a slightly different situation. A list of use cases. And bottom line here also is ethical decisions and permission from your IRB or whatever your ethics committee is called, which matter because when you're measuring stuff which may have real users, you may inject real traffic into your research network, or you may measure an operational network, then you really worry about privacy, and you may learn things about the questions you see there, that cause problems and so on. And ethics is not a completely, it's not a completely standing still thing. I mentioned, for example, in the adaptive trials in medicine, I was a bit shocked when I heard about these things. I was thinking, you're going to vary the treatment you give to people based on the distributions of success of treatments of other people during a treatment. I thought that was not allowed in medical. And they were like, well, no, actually it is, because the overall outcome for most people is better, even though for some people it's worse. But if you didn't do it, it would be worse for everyone. And this is like there may be cases, for this kind of thing. Actually, UK is doing an adaptive trial right now with vaccination program here for COVID, where we are varying the intervals between the first and second dose of the vaccine. And most people in the rest of the world think we're mad. But on the other hand, we've got 21 million people vaccinated on the first dose and now 1 million on the second dose. And if it looks like this works fine, we will have doubled the number of people we can vaccinate in the same period, clearly. So that will be a really big success. So that's an adaptive trial where the ethics was argued that there was a risk, but it was known to be fairly small. It turns out it's probably zero, so which is quite cool. But anyway, so what's the equivalent to networks? Well, I imagine if you were doing some experiment with self-driving cars and 5G networks, you might want to be super careful about how reliable your network is. Otherwise, bad things would happen. Okay, there's a couple of refs. I'm just done now. I mentioned a few things in going, and there's just some reference there. And somebody's kindly put the link to Mark's son's project video, which is so that. Thank you for that. That's. But I'm finished, so I'll stop sharing slides, and I guess I can take a couple of questions.
Okay, Thanks a lot, John. Very, very interesting, very inspiring. So we actually have a few questions in the questions channel. So I guess the first one is from Yuri. What is your vision on the current network cloud integration and merge? Also considering the cloud native approach promoted by 5G. So basically the integration between the networking world and the cloud world, I guess. I'm
not an expert in that. I understand the original reason for this was that the support for legacy cellular networks needed people to virtualize the radio access networks for the earlier networks, so they could then emulate it. And essentially, that's what the whole network virtual functions came out of that world. And then you need a sort of mini cloud infrastructure to run that on, because you need to vary the resources, as a demand for 3G access goes up, and at the bottom of every 5G cell tower, you have a rack of computers that implements a small cloud that can implement a sort of cloud RAN or whatever. And I mean, that's what my understanding of that world is. It makes complete sense. What doesn't make sense is to use a sort of general purpose cloud, like AWS or Azure or some other service, because by definition, the cloud resource for integrated with a network function has to be very, very low latency, and probably, co-located with most of the network equipment where it's, but I think that the economics of that, my take, and I'm not an expert in the, cloud RAN stuff, but my take on this, it also makes sense if you're thinking of building that resource as a not quite edge cloud, so near edge cloud. And that means you can avoid for applications, you can avoid a lot of backhaul traffic. So there's a really nice paper from people at Queen Mary in London on where Netflix put all their content distribution network servers, and they co-locate them with all the internet access points. So they have a large number of smaller servers, and they don't pay other people for big servers. So that's like a mini cloud, and it means when you streaming Netflix, you're typically getting it from a very nearby server that has lower network cost. And clearly, if you were a mobile provider, you want to support streaming video from Netflix for people seeing in the backseat of a car or train or whatever for entertainment, and you'd use the same resource. So co-locating stuff for that, where you have a rack with a couple of thousand CPUs, maybe 128 cores, you could get a lot of resource in one rack nowadays, and that could do both functions. I mean, there's a question though. I think if you're optimizing for energy, you might use different accelerators for the cloud RAN, where you might be doing some signal processing type work than if you're just doing streaming. So I buy the argument for why you want to do that. And again, I see it as one of the examples of some kind of near edge processing, but more large scale than just offload. So it's a good point. I don't have a feel for the right design of mix of what processing. I imagine you could use the same accelerators if you're going to transcode video for different streaming qualities for end users as you might use for doing some of the radio protocol work, if you're going to emulate some other protocol. But I don't know. It'd be a fun thing to look at.
Yeah. Okay. So in passing, I guess you also answer another question, that is the trade-off between federation and centralization in designing the research infrastructures. I think that was covered pretty well during the talk. A couple more questions about heterogeneity at the extreme edge. So what does it mean when you go to the individual devices too? I mean, when you want to federate the resources that you have also on very far edge devices.
So the problem there is actually something, there's another piece of ancient history. When we were doing virtual machines for the cloud, and we did the Zen hypervisor, the original vision was that was going to be the end user's machines that we virtualized. So the idea was everyone's laptop would be running code for somebody else. And the reason the virtualization was there was to do isolation between someone else's code and your own code. So you're sitting on your laptop, you're doing your word processing, writing your paper, compiling your application, and it would also be serving somebody else out on the net. And the idea was and now it turns out on most current devices that might be extreme edge would be, a smartphone or a tablet. The virtualization might not get the right performance isolation. It might cost you too much. Plus the asymmetry bandwidth might not work so well. The heterogeneity also was going to buy, because you're going to have all kinds of variants of ARM processors that are made by different people, and the support for virtualization to get isolation might not be the same. On the other hand, there's a lot of work inside both Apple and Google for certain, and I know other people as well, on getting better isolation properties because they want to improve the privacy of end user devices. They really want to be able to nail, so for example, in the Android operating system, they want to run that on top of a very small verified VM. That will really help, because then you can then do that isolation with a lot more confidence. And the ARM processors are going to have, the next generation has some pretty cool support for fine-grained access control as well. So that may help, but that won't help if you then want to exploit other resources and end user equipment, like you might have accelerators on the end user device. For example, Huawei phones have a machine learning accelerator on, and it would be nice to maybe use that for other people nearby. You know, somebody takes a picture, they want to, I don't know, it's a hard problem. Maybe it's just pushing things too far to decentralized.
Okay, well, one last question, I think, from Serge, actually. So basically, we are moving in a world where the network will be programmed by many, but operated by few, as it was also in the old times. So what is the main implication for you, I think, of having this distributed system that is operated just by a few players, but it's basically open for being programmed and controlled by many people, actually?
Yeah, this has been, I mean, Scott Schenker's original vision when he talked about the whole software-defined networking, he appealed to the right answer for that, I think. I mean, I was good. I can't quote him exactly, but the two things you have to be able to do, and one is you need to use the most up-to-date software techniques to isolate the behavior of different systems. So many people could program the network to provide very customized services to many people. And we've always wanted to do that with, you know, slicing Planet Lab, but this has to go right the way down to the bare metal to get the isolation between things. So then the operator just worries about resource use and charging for that. They don't care what the semantics of all these different complex servers are. I mean, they may implement some themselves, but you know, if somebody's using more processing in the network to offer some clever thing, that will just be part of their billing. But many people, you know, should be able to program the network in the same way we program apps for smartphones. There should be millions. I totally agree with that. But the task must rest in good, absolutely state-of-the-art software where you can do verification, validation, you know, performance prediction as much as possible. I think none of those things are 100%, but the tools we have for that are way, way better than they were 20 years ago. So it's definitely an achievable vision that we have to use all those tools. So that should just be part of our, you know, continuous integration. You say, have you verified this piece where it, you know, it really matters? And of course, you can sandbox things. You can verify a component and then put a wrap around and say this will now behave correctly. So you don't have to do exhaustive verification, but you still have to have a story about that piece. And I think that's where we can have fun with people like Nate Foster at Cornell, who's, you know, is a networking and a programming language person. Those kind of people, we need to have more people, train up more people to do that cross discipline kind of thinking. Okay.
Thanks a lot, John. There are other tons of questions that I'm sure people would like to ask you, but we are running out of time. So thanks again for your inspiring talk. It was extremely useful for us. I leave it to Serge, and we have a break now of 10 minutes, I guess.
Yeah, thanks a lot, Andrea. Thanks a lot, John. It seems, looking at the picture of your talk, that you have been cooking a lot during the lockdown. Nice gone already. Okay. Good. So we have actually a 5 minutes break just to move things here and there and bring the speakers of the next session on stage. So please stay tuned. We'll be back in 4 or 5 minutes.
Hi, you can share your screen.
Yes, I can't find PowerPoint sharing button. Can I just share the entire screen? Is that
You can share your screen, and then you can go to application window and choose the specific application and file that you want to share.
okay.
Okay.
Like this? Do you share my PowerPoint?
Yeah, exactly.
Okay.
And you can go to presenters mode, so to have a full screen of this.
Okay.
It's excellent.
And is my face also shown on camera?
Yes.
Okay. I can't see myself though. But
you look so great.
Okay.
It's almost midnight. Thank you so much. Again, I know that I could ask you to stay late at night because I see you are still in the office.
Yes. Actually, I went home once and I had a dinner with my daughter, and then came back to school.
Yeah.
Because it's very nice to see you, Serge.
Likewise, it has been a long time. So we have to organize this virtual workshop just to set up the opportunity.
Yeah. So you said that I have 15 minutes.
Yeah. So the idea again, and I know it's a little bit challenging, but because everything is virtual, the people cannot really handle long presentations. So the idea here is to have basically a 15 minutes presentation as we discussed, so that we leave opportunity for questions and discussion among the speakers.
Mm-hmm.
I know that it's for you, so you'll have 15 minutes, and then we'll manage questions for you, and then of course I understand you can leave because it's pretty late.
Okay, thanks.
So we'll wait 3 minutes and we'll start.
Okay.
So we're very happy because we had about 120 participants.
Oh.
We have more than 100 connected still. So that's good for us. Even.
That's very nice. That's good for me.
Yeah.
Oh, so Serge, my daughter is now in college. She's interested in going abroad, but it's because of COVID-19.
Yeah.
The first choice was at your place because she was interested in living in Paris. But unfortunately, this situation doesn't allow us. I mean, we were very worried if we send kids to the foreign countries. Well, Japan is not the safe place either, but still.
Yeah, no, this is really unfortunate, and I won't advise to send her, but she will have other opportunities, and we'll be very happy to host her here, of course.
Great, thanks.
Okay, so ready. We're very pleased to start this international session. That's really, really important because this is really a broad initiative, and this is a challenge for the community. And again, the idea here is to see what is happening in the different locations with respect to addressing this kind of challenges. And the idea is also to understand how much we can share with respect to, of course, the software, the hardware, the knowledge, the data, the experience. And this is a long way, so I'm very pleased to have 4 guest speakers here who are very representative of what is happening. And this is my great pleasure to welcome Aki. Aki Nakao is the right person in Japan if you would like to understand what is happening in networking at large. And of course, he will give a very short presentation, but he will be very pleased to address your questions. So Aki received his BS in physics at the University of Tokyo, but then he spent quite a long time in the US working with IBM, first in Texas, Austin, and then he received his master and PhD from Princeton University, and this is where he started also working on Planet Lab and all this type of infrastructure, and I had the pleasure then to meet Aki. So he's a professor at the University of Tokyo doing a lot of different things, from UAVs to platforms to 6G. And again, thanks a lot, Aki. It's 11 p.m. in Tokyo. I know that you are still in the lab. So thank you so much for sharing your thoughts with us. We know that Japan has always been, ahead with respect to some technological development, but the situation is getting, of course, more and more difficult and competitive. So we are very happy to listen to you and provide the question to the audience if they would like to ask some thoughts with respect to your presentation. Thanks a lot, Aki. Floor is yours.
Okay, thank you, Serge. We are, good friends for a long time. And thanks for inviting me to the first Slices workshop. It's my pleasure to contribute my slides and presentation to this workshop. So my talk title is 6G, the ultimate customizability driven by democratization. It's a kind of cryptic title, but I hope you can understand at the end of my talk what it means. So because the Serge introduced me in a very nice way, so I don't have to repeat myself what I'm up to these days. But as you can see from this slide, a lot of 5G and beyond 5G. So we are, we started doing lots of mobile networking, and these days, the Space ICT Forum is an interesting forum, and there. I'm working on the satellite communication and combined with the 5G and beyond 5G. But as a Serge introduced me, so I came from a programmable network, softwarized infrastructure of communication. So, I'm combining this softwarization and this 5G and even satellite. So that's what we are doing these days. Okay, today let me talk about private network happening in the mobile world. The local 5G, so it's sort of a private 5G in Japan, and we try to use the white space for private network. So Japanese government decided to allocate a frequency band, some frequency band to people like us, the regular people, not the telcos. To obtain a frequency band to define our own private network, especially 5G and probably beyond 5G. So I see this movement as, we are calling it democratization of telecommunication, because democratization means the action of making something accessible to everyone. So, we're trying to make a radio frequency license available to everyone, such as, Japan did a local 5G, but in the other region of the world, so they are doing the private 5G, allocating license for non-telecom people. So I'm positing that the divergence and inclusiveness, including everyone as a player for defining telecommunication and the key drivers for innovations for next generation networking, especially 6G. So I can repeat this message by using the slide. Public network is evolving from 5G to 6G, but because we have democratized network, so-called local 5G or private 5G, we can customize our network, because we can define the usage of a frequency, this frequency band, not necessarily following the 3GPP standard precisely, but we can add, the customization to the problem that you have. And for example, low-cost mobile infrastructure, local 5G in the box, uplink optimization, low power operation, and custom security. You can do all kinds of innovations because this local 5G is for you, and you can make it programmable and add some customization. That leads to the innovations towards local 6G, and you can collect the good ideas from the various innovations that happen in the local region, and we can extract the common features and try to define a 6G. So this is what we are doing these days, trying to develop our own private network innovations and trying to reach the goal of 6G. Okay, let me introduce one project because due to the time constraint. So we are trying to do a local 5G in the box. We take a software stack of 5G and put that into the regular PC box and generate into PC and try to make a RF system. So this is my lab, and this is a custom-made base station of 5G, and this is made by software running on top of Intel PC. So and you can try to optimize it, downlink and uplink, because some people like to do uplink optimization. For example, you take a video, very fine grade video, and try to upload it to the cloud. But usually telcos optimize their mobile network for downlink, because a lot of people are watching YouTube and downloading data from the cloud. But in the local region, we see a lot of use cases in which upload optimization is useful. So we customize our base station so that we can achieve up to like over 200 megabps in the upload. And using that, I brought this software based base station to oyster farming. Why oyster farming? So this is a very unlikely area that you can apply the ICT to this kind of business, fishery business. So I like to do some strange things that no one else is doing. So we brought this softwareized box and used that for solving this fishery business problem. So we went there, and so we did a lot of field experiment. I don't have time to explain the detail, so let's take a look at this picture. So we talked to the fisherman, and the fisherman's problem, one of the problems they had is that this oyster farming. So they have to check the growth of the oysters hang from the oyster rafts. So, but doing manually is a lot of work. So we decided to use an underwater drone, and we control that by 5G and take a video stream by the camera attached to the underwater drone, and send it over to the fishermen waiting in the seashore. So why 5G? We have to send a large amount of data uplink from the underwater drone, and also why 5G? One of the reasons is that the URL is low latency. You have to be able to control the underwater drone by low latency. So what we did, I can flip the slide because I don't have much time. So we brought our custom-made base station there, the fully handmade by our lab, and tried to measure the signal strength from the base station to the farthest point. It's about 600 meters, but we can still do a communication. Again, this is not and commercial product. This is handmade and we can run everything on the PC. And some free pictures of our base station, underwater drone, and doing the video streaming. I can show you I hope that this video stream can be, delivered nicely on this, virtual conference platform to the European people. But this is the underwater drone video. You can check the oysters. By the way, I love, oysters from this region. So there are a lot of people who like the oysters, but this is the first time for us to see underwater the very fine, pictures or videos of the oysters hanging from the rafts. Well, we need to be able to send this, video to the seashore. So that's the reason why we need a large bandwidth, and 5G is there, because the fisherman's boat is just far away from the seashore, and we have to use the wireless communication there. And at the same time, we need to do a precise control of the underwater drone. So that's why we need a low latency. If you want to do this with the commercial 5G, we may face the problem because there's not enough uplink bandwidth. But because of the customization we did, we can send this video to the seashore because of the large uplink capacity. Okay. And another thing that we found is that this dirty the bottom of the sea, and all these oysters shells are accumulated over time. And as soon as we saw this video, so we are urged to clean up the bottom of the sea. So this is another observation that we did with this underwater drone. Okay, so this is a slices workshop. So we can add a slice idea. We like to isolate the underwater drone video streaming and the drone control and the underwater drone sensors. And we have to be able to do application-based slicing. So this is another customization that we can add to the 5G base station that we did. And again, this is another technical video, but we can break down the traffic by application, and we can precisely control the QoS of each application traffic. Okay, we can talk about it if you are interested, how we did it, but we can just skip that. Finally, so doing this, we would like to do 6G eventually. So there are several directions that our government decided on, but I'm interested in bringing all these innovations like low power, ultra security, autonomy and scalability and all that, combining satellite communication with the local 5G, etc. But it's all coming from our innovative mindset, but that mindset is coming from the customization, I believe. If you like to see our activity, more of our activity, you can go to this website. This is top page of the University of Tokyo. I'm leading next generation cyber infrastructure initiatives, and there we have 25 projects towards the beyond 5G. In other words, it's 6G. Okay, so this is the end of my presentation, and I said a lot of words here, but in a nutshell, my advocation here is that the 6G is coming from the ultimate customizability driven by democratization, like as in the local 5G. Thank you very much for your attention. Now I can take questions.
Thank you so much, Aki, and thanks for playing the game of staying within your time budget. It's a huge amount of information and, of course, things that you are doing. I knew you were doing drones, but now you go underwater. So, of course, please, this is for the audience. You can ask your questions on the question stream. Aki, I have a first question, which is, of course, in Japan, they are very strong stakeholders in this domain. And so when you talk about democratization, what is their perception? Because usually we know that it's not the first, thought that they might have.
Yes. So, so of course, telcos like to, do the regular evolution path, like from 5G to 6G, and bringing, doing the white papers and doing the standardization at FCCPP. But at the same time, people like us, the university professors, they like to do like test bed, like research. You develop a test bed and try your new ideas, and it takes time. Usually, it takes time for us to bring those technologies into the production network, like commercial network. We experienced that when we developed Slice idea in Planet Lab and Planet Lab Europe, right? So, so we sort of bring that kind of experience into mobile network world, and so in that sense, so people's response to this democratization idea is various. But if once you are given this softwareized environment, and you can develop your own mobile network, so then, for example, graduate students and people like us, who like to develop things by ourselves, they are happy to bring innovations. And then, it's now it's turn for telcos to pick up technologies and try to develop, deploy, and commercialize it. So I'm just proposing, another way of doing, innovations, and we are calling that a democratized telecommunication.
Yeah, of course, trying to explore how this could be then taken on board by the stakeholders. We have a question, the same question actually from Yuri, about your vision on current network cloud integration and merge, also cloud-native approach promoted by 5G.
Okay, nice question. So once we softwareized everything, like a mobile network base station that I showed today, some of them could move to cloud. So we are talking about, coordination of infrastructure between cloud and edge and extreme edge, which is the base station. So I like to, well, Planet Lab is actually coming from cloud slicing, bring that slice idea to the network. And then now we are doing similar things to the mobile network and, to the extreme edge, like a base station. So everything is now cloudified. So as you said, network cloud integration is actually happening here. Everything can be cloudified. So that's the, the real gist of slicing, I think.
Thanks. Yeah, it's a very clear statement. John was a little bit more mellow, but as he said, he's not really working in this area. I know you have been involved since a long time. So a question from Andrew. Hello, Akihiro-san. How does the direction your 6G research is driven? How do Society 5.0 goals affect that compared to other countries?
Yes, of course. I actually removed one slide about the SDGs and the Society 5.0. And the reason why we are bringing ICT into a local region and to showing, application of ICT to oyster farming is actually, driven by the Society 5.0. Everything is moving from, manual labor to, digital world. And those people who didn't have a chance to be exposed to ICT is now moving to, digitalization of everything. So even the oyster farming, they can, use the idea of virtualization, slicing, and we can bring those 5G or maybe beyond 5G, 6G technologies into those fields. and digital transformation can happen there. So I like to see that. Thanks for bringing this question up, because I wanted to say, Society 5.0 and SDGs, those are driving factors for our research too. Yes.
So meaning that you have this debate about, energy consumption or the impact on the environment or digital sobriety. This is also an important topic.
Yes. So as I said, one of the customization that we are trying to achieve is, eco-friendly, like, environmental friendly, low power base station. And I didn't show, our work, slides about our work on, low power base station yet, but we already developed this, battery powered base station, which is very, very low power, but enough, bandwidth that you can use, by this base station. So one of the directions that our government decided on is low power mobile infrastructure. That's one of the goals of 6G in Japan too. So I totally agree that the environmental friendly and also low power consumption should be one of the 6G goals.
New question popping up from Frédéric. With open 6G networks, what is your vision about autonomous coordination between actors?
Okay, so actors, maybe, so the actors could mean many things, but one of the 7 goals that we decided on about 6G is autonomy. So we try to bring AI and machine learning techniques into a network, and I think Serge and all the colleagues here, trying to do the same thing. But autonomous coordination of components, like software components, are already studied. And if I had a time, I would have been able to introduce those activities. But again, this is important direction of 5G or 6G networks.
Aki, a question about this cyber infrastructure that you mentioned. It was one talk. It has always been a big concern, and this topic is becoming, of utmost importance because of, sovereignty and those kind of issues. And it has been a question how far we can go, by merging test platforms, dealing with security at large and dealing with protocols. So this platform is meant to support both, or it is really focused on cyber, as it was the case for Decay in the US?
Okay, so that's a very challenging topic here. Okay, so the so the security and privacy. So that's another customization that you can do. So for example, if you can customize your software-based base station, one of the things you could do is add a stringent security to your base station, custom security. No one else is using those encryption, privacy scheme, because you can define your own encryption scheme and the privacy system. So if you need the very stringent encryption system, you can integrate that into your own infrastructure. So that's the one customization you can do, right? But as you pointed out, no matter what you do in your system, always the privacy issues is coming after what you developed. So I think US and also Europe are advanced in terms of this topic, and but Japan and also Japanese government is caring about this cyber the physical system we have to care about the data, after we secure the data, but also we have to deal with how to use this data, how to protect one's privacy and all that. That's a separate issue, and it is very hard to attack.
Okay, thank you, Aki. Really highly appreciated. Besides the fact that I really enjoy seeing you and seeing all those activities that you're developing. Thanks a lot. I hope we'll have the opportunity soon to meet again physically, and take good care of you. Thanks so much.
Thank you, sir.
Bye-bye.
All right.
So we're going to hand over now to the other side of the world, going to the US. So we have Abhimanyu Gosain on stage with us. Thanks a lot, Manu, for joining us.
Hi, good evening, sir.
So I'm going just to give a very short introduction to Manu. Many of you know him since long. So he's a senior technical program director for Power and director of industry engagement for Institute of Wireless Internet of Things at Northeastern University, and he is worth $125 million. 100 million public-private partnership for the NSF platform for advanced wireless research. So Power is going certainly to touch base a little bit on that, although it's a big initiative, and lately joined the $25 million DARPA Colosseum program has also been included. So he is really involved in all initiatives, mostly dealing with open source software in a way or another, and I think that's really, really important. So Open Air Interface is one, Magma Core Foundation, ORAN, Telecom Infra, and so on and so forth. So I won't spend too much time. He is really instrumental in not only, of course, being steering with others this Power initiative, but also with the global vision of how things should be developed. So Manu, thanks a lot for joining us. And the floor is yours. 15 minutes question, and then 15 minutes presentation, and then 15 minutes question. Thanks.
Thanks, sir. Just a quick audio check and screen check. You can see my slides. You can hear me. You can see me.
Seems everything is perfect.
Perfect. Thank you. Awesome. Well, thank you again for having me, and coming to you from nice and cold Boston, Massachusetts, here in the US. And I want to sort of take this opportunity again to talk about primarily research infrastructure. That's sort of my strong suit, but also start to think about and lay the foundation, or at least present a vision of how do we think about coalescing the research agenda and the research infrastructure needs as we look at beyond 5G to 6G research. So Sajid did a great job introducing me again, as always, and I just wanted to sort of put a lens through which I'm going to present the beyond 5G 6G work. So primarily our experience and the programs and projects we lead here in the US have to do with development of large-scale research infrastructure, mostly focused on wireless, Internet of Things, wireless research infrastructure, and end-to-end communication systems looking at 5G and beyond 5G. And in that sort of purview, we've been able to coalesce and participate and stake a leadership position in multiple these alphabet soup acronyms that you've probably seen of, some of which you've contributed to or follow. Open Air Interface, ORAN Alliance, Open Networking Foundation, Telecom Infra Project, and the most recent, the Magma Linux Foundation that is looking at Open 5G core programs. And then DARPA Colosseum, being the world's largest channel emulator, adds to the portfolio of the research infrastructure we own and operate and provide and make available to the NSF academic community. But here I'm just going to shift the focus a little bit forward-looking and think through 6G. And we thought this was the right time. I think this is a very opportune time and venue to start discussing about 6G. But we took a little bit of a leap of faith and try to converge and bring together community, which is what this workshop is also trying to do, and start to think about and explore what 6G would be. So we, alongside our industry partners at Interdigital, organized the first annual 6G symposium, which we'll be doing next year again. So what I'm trying to get across, at least from this slide, is people seem to be ready to talk about 6G. There is the hype versus reality. There's that school of thought that 5G hasn't necessarily been operationalized. But from a development and research perspective, we are looking at release 17 and 18, which, according to the people who work in standards and 3GPP, you're almost coming, you've crossed the halfway line in terms of defining and specifying what a 5G network would be. And at least according to some experts, and just take it on face value, release 20 onwards, people might be ready to think about 6G. So just a quick, numbers of what people are, thinking, looking, discussing about 6G. So about, 4,225 people all over the world. Yes, small representation, but again, this was a virtual event. Very happy and satisfied to see this, and I'll try to distill some of the thoughts that came out of this forum with leading industry, academia, and federal experts from all over the world. So this is sort of the right time to start talking about 6G. But again, as always, you can't look at the future without sort of looking in the past. And what are we looking at when we look at current 4G and soon to be deployed 5G networks? Again, the same old story around monolithic architectures, hardware vendor-based, vertically integrated, hard to update, improve, reconfigure, vendor lock-in. This one I may spend 1 second on, which is geopolitics. And I think the sovereignty part was also alluded to in earlier talks. This I see as a big red flag for forums such as these, collaborations across countries, transatlantic, Pacific, Europe, Japan, US, Asia, Brazil. And we feel that this is actually causing some sort of fragmentation and stress, especially as nations begin to flex their muscle. And primarily 5G is being used as a geopolitical tool. Does not bode well for research collaboration. So a key point for 6G, or as we look at enabling technologies, partnerships, and models of engagement for 6G, we have to be very careful about not letting this political influence affect us. But this also maps onto somehow how governments are operating, and most recently around the notion of open radio access networks in 5G beyond 5G. There have been investments and exclusion policies, not just from the US, but also in international forums. Japan and Germany and France also have individual funds propping up local companies, which is great for those companies, but necessarily causes some sort of fragmentation when it comes to technology and architecture. This is sort of one-line summary, and again, people can challenge me on this, but from my perspective and from our perspective, from the team I represent, we're still looking for 6G wireless systems to really deliver ubiquitous, ultra-reliable. URLLC is a theme in 5G, but we all know that has not been come to fruition, has not been developed or deployed. And to provide near instantaneous gigabit connectivity between humans, and the most important things, between machines. So humans are out of the loop, and the hope is that 6G will be providing technologies that allow for machines to communicate at high speed and autonomously. So a quick sort of a portfolio rundown of what we believe beyond 5G and 6G enabling technologies are going to be, and what we are sort of looking at. Virtualized RAN, very, very hot topic right now. Traditional approach on the left, what's happening on the 4G side, and what is being touted or has been developed in the past few years around virtualized radio access networks, where you have functional splits across the radio antenna element, the RF front end, or on the baseband side, and further functional splits between where the intelligence in the radio access network is going to lie. And this is basically just a simple picture oversimplifying where the base station is, where the remote radio head is, and where the actual compute or digitization of the analog signals in the baseband processor is happening. So very important. We believe this is going to continue as it matures and develops beyond 5G and into 6G. O-RAN Alliance is, this is sort of a high-level architecture picture of what is being discussed, developed, specified as we speak. quick sort of rundown. I really don't want to get into the details. I'm presuming majority of the audience is somewhat familiar with these topics, and if not, I do highly encourage you to sort of go and look at what's happening in this domain. But primarily, this is a very rich ecosystem that is basically at a high enough level, just talking about disaggregating to increase the vendor ecosystem for radio access networks. So sort of breaking the monopoly of traditional tier 1 OEMs by providing open interfaces between what's called the central unit, which is sort of far away from the radio unit, the distributed unit, which is a little bit close to the radio unit for more of the real-time functionality, and the radio unit, and the ability to have multiple vendors provide different parts of the solution, and then have a service management orchestration framework with a similar concept to what we use in SDN today in production networks of a radio intelligent controller for real-time operation optimization and definition of radio access networks and over-the-air interfaces in future kind of networks. That's the good. Horizontal disaggregation and abstraction is the good. What's not good is fragmentation. We are seeing, in addition to the O-RAN alliance, multiple different alliances, and this also touches a little bit on the geopolitics of the race towards the next G. We're seeing multiple different initiatives and efforts that we somehow are not seeing converge or come sort of together. O-RAN Alliance, again, seems to have the lead in terms of defining the specifications. What you don't see here is 3GPP, because that obviously is all-encompassing, and how this all shakes out and how that relationship sort of manifests itself, which will effectively, at the end of the day, affect all of us, is important. Multiple of these alliances are doing different things. Just want to point out the NTT Docomo ecosystem in France, Open RAN Policy Coalition in the US, Dish, and these are non-traditional partners, Satcom companies, Ligado Networks, and Dish, that are now looking at 5G and beyond 5G technologies with their own flavor of open radio access networks. So this sort of gives me pause, and I want to sort of bring this to the attention of this audience as well, is the fragmentation, which is sort of, again, something where we're seeing different approaches or different implementations to a very simple concept, which is quite noble, but we're seeing a little bit of obfuscation on how this is actually being implemented in the wild. Really quickly, cloud, so 6G beyond 5G, some of this stuff is in production. So SDN NFV has been for a while productionized. Cloud native approaches to 5G and beyond 5G, this is sort of almost a given. Public cloud players are going to have a big say in how future networks are deployed, how they're operated. And I heard an earlier comment from John during John's talk and Serge's comment around programming will be allowed to plenty of people, but the actual operations is going to be in the hands of quite a few of them. And how do we realize, and how do we actually decouple technology from the architecture is going to be key. And that's where a lot of the service management orchestration techniques that we can borrow from the public cloud players will have a huge impact and will need to be defined and discussed and debated as the standards evolve towards 6G. This is a hot topic, again, conquering the spectrum. So right now for 5G, Wi-Fi, we are looking at what we, at least where we draw the line here in the US, may have differing opinions in the EU and other places, is at 95 gigahertz. So right now, plenty of spectrum that's been auctioned and some technologies that have been developed, specifically in millimeter wave, and looking at Wi-Fi 6 at 2428. And you can sort of read the list. Where I want to focus is where we're headed next, especially in the US and EU. There are efforts and initiatives looking at above 95 gigahertz, and the consensus seems to be that 100 gigahertz up to 1 terahertz would be a place where 60 devices will actually operate to provide the connectivity and latency requirements. But as always, there's a big elephant in the room, which is propagation becomes immensely challenging because the antennas are smaller, absorption enters the game, blockage reflections. Again, this is not a technical talk, but I just want to make sure that these are the kinds of issues that we're going to need to look at. And then we're going to have to look at partnership models as to how do we address this. I mentioned, again, just to jump back, some EU and US-based projects and centers that have been kicked off that are looking at these technologies. There are different alliances that are looking at this, but this still needs to have a solid body of fundamental research work before this can actually be looked at from an industry perspective, and then the pragmatic issues of actually deploying this. And then again, next one, AI/ML. So AI/ML, we're seeing huge advances in deep neural networks, reinforcement learning, and generative adversarial networks, which are enabling disruption. So again, AI/ML has its fingers all across the stack, but AI/ML, as everybody knows, is only as good as the data that is useful for training and inference purposes. We really see research infrastructures as key assets to generate and make available large open data sets all across the stack, but primarily for wireless communication systems. So both synthesized data sets, but also over the air, large-scale outdoor testbed generated data sets that can be made available for the community. And AI/ML is not ubiquitous in terms of solving problems for everything. The human element is still quite important, and it's not a substitute for modeling. And you essentially need a lot of rigor and developing and training these models in combination with different classical tools. The point I'm trying to get across is AI/ML is its own domain, and its application in 6G is going to have to be clearly defined. And primarily where we see the biggest benefit is in the reconfigurability and optimization of networks and of air interfaces, looking and sensing what's happening in its environment. So a very, very cool area of research. We have lots of cool projects and work going on in this arena, and significant investments that we're seeing globally. And this seems to be the clear arms race for the next decade. Just to sort of connect all of these things together, from open radio access networks to AI/ML to cloud native software centralized approaches, canonical sort of architecture picture of what a 5G network will be. This is not what's in production right now, as much as operators and vendors want you to believe that, but this is what we are sort of playing with in our labs right now. And what I want to talk through are 3 different AI-enabled loops. Really, really low latency loop all the way to your right between the radio unit and the distributed unit, which is going to be very important with the large amounts of information and digitized data that comes from the radio unit into the DU. And how do you actually separate some of this functionality, and then how do you optimize it at each layer? And how do you then implement these cases at the bottom, slicing, beamforming, traffic steering, and network optimization around this? So this sort of uses everything I just talked about, right? So you have the ability to instantiate all of this on commoditized infrastructure with a softwareized approach. All of these different elements have clean, open interfaces that need to be defined. And then you have AI, which allows you to deploy artificial intelligence, machine learning at different scales around latency, around the amount of data that needs to be consumed, and the decision-making that needs to happen in a real-time fashion in deployment 1, moving into the near real-time rig, and then a heterogeneous combination where AI is at all parts of the network, from the non-real-time piece, which is less latency sensitive, moving to the right and moving to the more real-time latency applications as you talk about slicing and optimization. So this is where it all converges, comes together, and the hope is that this is going to be a springboard of where these technologies are going to go as we start to discuss beyond 5G and 6G. And clearly we need significant investments and collaboration. Without that, I don't think we'll be able to realize this at a global level. And then last one, just food for thought, quantum computing. From my perspective, it's a paradoxical choice where essentially the good is quantum encryption, storage, blockchain technology will be really, really cool because this really has an impact on security. And that's the con. So we can live or not live without it, but quantum computing is here to stay. It's not realizable today, but again, over the next decade, I feel this is going to be something that's going to need to be discussed. Last topic that I didn't pay attention to, and I realize I'm a minute over time here, is security. Zero trust models, zero trust architectures, moving away from perimeter defense and basically looking at these open paradigms as a place where network operators need to be moving towards, again, from a zero trust model. So moving away from closed vertically integrated solutions, and seems like the equipment vendors and the major players in standard setting organizations are moving in that direction as well. And security is cross-cutting, affects all of these places, from where you want to be in the spectrum, where you want to be in the network, what kind of air interface you want, what kind of AI/ML models you want to use, and what sort of radio access network or management orchestration techniques you'd like to use. I realize this is quite a mouthful, a lot of different places and a lot of different ideas, but I sort of look forward to your questions, and I cannot stress the importance of research collaboration and partnerships in helping realize these techniques and technologies. For more information, please check out these resources. And again, I appreciate your time, and I look forward to your questions. Thanks.
Well, we do appreciate your time, Manu. It's a very dense and informative presentation. Thanks for, again, staying within the time budget, but we have opportunities for questions. I see a first one, which is about the IoT dimension. So, for instance, what will protocols such as NB-IoT become with respect to the development or perspective of 6G?
Yeah, great point. So from IoT or NB-IoT, I think the key driver for that are going to be use cases. I didn't hit on that because that's already being discussed right now. So the biggest drivers that we are seeing, and actually this talk was less about power, more a little bit looking ahead, but we're looking at implementing and realizing application domains primarily around precision agriculture, where IoT technologies are being stress test deployed today. The evolution of that sector, and now most recently, again, keeping an eye on where standards are moving, it has the inclusion now of non-traditional partners, John Deere, big, large agricultural companies that are looking and influencing the direction of IoT and the kind of IoT architectures that can be deployed. But from my vantage point, it's not necessarily the technology that's going to drive the innovation and change. It's actually the application drivers and the key use cases that are going to pull technology into sort of solving the issues that they have. And NB-IoT is just one flavor. Again, this ecosystem is quite rich, fragmented, and at the end of the day, it's going to be what's going to be implemented and what benefit it may provide beyond your traditional approaches that these non-traditional sectors and industries are sort of looking at. So that's sadly the reality. But I feel this is a good time to be sort of involved in this ecosystem and sector, because you're actually bringing together people who don't even speak the same language. And sort of 5G has been the first place where everybody has a seat at the table in helping define and coalesce. So I appreciate that question, I think, but it's quite loaded. So I'm not sure I did a good job with that, but
okay, thanks. More questions coming. So one about quantum computing. Of course, often we have questions about, if you pretend to look ahead, then you should somehow integrate this new dimension of quantum. And so Bartek is asking whether, so you mentioned risk and cons. Is quantum key distribution a solution for your concern?
Yeah, that's a great point, and that's a key sort of technology area that we're looking at now. Again, quantum is a paradox, at least in my mind, because yes, quantum key distribution helps with encryption, helps with some of the security concepts, but that also exposes additional attack surfaces and threat models that we don't have right now. So from a traditional perspective, quantum key distribution affects probably one particular silo or one particular sector of security, but from an overarching zero trust security model going forward, and the architectures and the technologies that will make that happen, I still feel the decision is up in the air as to how and what sort of an impact this will have. But it is a start. It absolutely is something that's being discussed. It's being realized, at least in the federal ecosystem, and the primary adopter of technology here in the US being the Department of Defense, significant investments under the 5G umbrella for quantum key distribution projects. So we're seeing that, and we're seeing significant attention to that.
Thanks. There is one question from Peter about experimental facilities. So if you if you evolve from 5G to 6G, do you expect that the need will grow as well? You will need more and more facilities to support the design, or?
Yeah, so that's such an opportune question at this time, and this is something that our federal ecosystem, at least here in the US, is grappling with, even in the context of 5G. So more is always better. That's at least, I think, our perspective. Shared facilities, large-scale infrastructure, again, providing a common benchmark system. That's what experimental facilities do really well. Democratizing the access, we heard from Aki, that's another key area we're looking at. I think as we look at 6G, primarily as you sort of move away from the radio, because the radio is extremely specialized and you're going to need significant investments all the way from the device level up to different architectures that you'll need. And for that, you may need specialized, and there's already investments, as I mentioned, in the US Aerodyne project, in the EU Aerodyne project, and in the US SRC Com Center work that's sort of happening. But the cloud native approach, or the commoditization, softwareization on the network and the cloud front, that still remains to be seen. So public cloud companies are sort of encroaching upon and building large scale facilities and building solutions that can be instantiated on public clouds. The jury's still out whether research infrastructure will need to be diverse enough or forward-looking enough, and we need to make a case ourselves as to, do we actually have that value proposition on the cloud and the network and the data fronts, rather than being subsumed, or rather than letting the public cloud companies, the big four companies, dictate what's important to our community or not. So I'm always in the favor of having a much more snowflake approach for research infrastructure that's unencumbered by what's happening in industry, that allows us to explore fundamentally different approaches and techniques and architectures. But that's still that debate is really ongoing, and we're really watching it unfold as to how that's going to impact what research infrastructures are going to be developed, what's going to be the direction that at least the US federal ecosystem decides to take, whether to work with large-scale research infrastructures, involve industry in public-private partnership models, or sort of seed to what's going to happen in the industrial ecosystem. So really don't have a clear answer at this point, but it is a very, very hot topic.
So maybe just as a follow-on of this question, so of course we're aware of the power nodes, and you have two basically addressing core network technologies or whatever network technologies, and then others dealing with mostly the vertical, so the application. But how do you foresee then the articulation of the power node with respect to beyond 5G and the question that you have been mentioning in your talk?
Yeah, so where I think the power platforms, again, to take you back in time, the genesis of the program was in 2017, and it was technology agnostic. So the platforms, the first two platforms, were built to be a little bit amorphic in terms of the architectures that they were going to be supporting. So primarily they're looking, and they've been working with commodity off-the-shelf radios and programmable infrastructure, both on the cloud and the networking footprint. We feel pretty comfortable that, adapting those architectures, and again, this is the key point, is separate the technology from the architecture and the infrastructure. So with these platforms, where we are, or how we are thinking about building them for longevity and to protect them from obsolescence, because these platforms were large-scale investments and we don't want them to be obsolete in 2 years. So the idea was, from day one, the bet was to work with commoditized infrastructure, even though we were going to sacrifice performance, hardware acceleration, real-time work, but it allows you a platform and a place to experiment with different kind of techniques and technologies. The idea is that everything we build is modular in approach, so things can be swapped in and swapped out. To give you an example, we have millimeter wave radios today that are 28 gigahertz and 60 gigahertz. But there's already talk about moving up to 120 gigahertz and working with some forward-looking partners to bring in those technologies, bring in them into these platforms, and that primarily affects how these platforms are going to evolve as they move into the future. Right now, they serve a need for 5G. And that seems to be the topic area, and that's the direction they're being pulled in. But to sort of explore or expose the playbook to this forum here, from day one, these platforms were technology agnostic, and we were building on these principles that I shared here in terms of openness, open interfaces, software-defined infrastructure, and the ability to reprogram the architecture with whatever technology comes next.
Excellent. So there is one question from Yuri. There are claims about low latency of 5G networks. So Yuri has seen numbers like 30 milliseconds. What is this? Delay or latency? Distance that are covered and so on.
So if I interpret the question, is the question around, this is my interpretation. If you can correct my interpretation. So you're asking about or talking about the low latency, ultra reliable URLLC kind of paradigm that's being discussed in 5G. Is that how I interpret that? And what's that 30 millisecond number? Is that
the question is
end-to-end network latency that you need to satisfy, or?
Yeah, what does it mean? Is this an end-to-end latency, and what kind of distance that is this kind of latency is involving?
So, I mean, if you look at sort of the picture that I drew, which showed you the different kind of latency loops from the radio to the distributed unit, where the digitization first happens of the analog signal, those are sub 10 milliseconds. And as you move up the stack, you're moving up into the central unit, then you're hitting the edge network, and 30 millisecond is still pretty significant. You can meet those in an edge kind of a deployment where some of your core network functions, like the user plane function, are co-hosted very, very near where the actual radio has been deployed. And that's sort of the approach. Now, have people done that successfully beyond trials and proof of concepts? We haven't really seen realization of URLLC, and that's why I want to bring back, in my definition of 6G wireless systems, the word ultra reliable still sits there, because I don't feel that in the 5G domain we've done justice or actually been able to realize those kind of latency metrics that will need to be accommodated for future needs. So 30 millisecond, etc. Again, in a pragmatic, practical system, it depends, depending on the right conditions, in air quotes, with an edge deployment, really very carefully orchestrated and managed. To meet, if you have that as your metric of success, you can tune the parameters to sort of get there. But has it been done using 5G URLLC definitions? I don't think so.
Thanks, Manu. There is one other question from Andrea. Can you elaborate more on how in power you see the convergence of AI and networking in both AI for networking and networking for decentralized AI?
Fantastic question. I think I had a slide, and for some reason I believe I took that out. But if you can just, I can paint a picture for you where our common currency across the power platforms now, and what we are moving towards, are containers. So these are your softwareized, self-contained instantiations of different network functions and network elements. What we are seeing in the AI model is within those containers, being able to deploy them across the different kind of platforms. So that's sort of the realm of softwareization and the ability to portably move these containers from one testbed to another. The key thing around AI/ML is data sets. So what these power platforms have been able to do are collect data sets from RF measurements they're able to do in the wild, given the large footprint they have and the diversification of dense urban all the way to rural environments. Those data sets, those RF measurements, purely and RF and network both, have been publicly made available by these platforms. Those are ingested, and again, just taking you through that journey on power infrastructure, and I want to include Coliseum as well, because that primarily was built as the first instantiation of intersection of AI and radio. So in Coliseum, we take those RF measurements that have been taken in the wild, that have been digitized, large amounts of IQ samples. Those are ingested back into the Coliseum environment, and we develop what we call scenarios. So these are virtual worlds, virtual representations of the real data collected on the Power platforms. This information and these data sets are annotated by what we like to use called SIG-MF, which is a standard specification that came out of the NTIA, which is National Telecom Information Authority. We annotate that data, and I'll be happy to share the links and add them in a refreshed version of these slides I can send over to Serge and team. But primarily those data sets are taken, they're ingested, they can be used to train your RF transmitters or your network elements. And from there, you can deploy this experiment in the Coliseum environment in a virtual scenario that is a virtual realization of the actual physical power test beds. Then you have different form factors of compute. So we have GPUs, FPGAs, CPUs that are co-located on and 128 of these radios that allow you to sort of test all the training that you've given your AI model, and then allow you to sort of make either inference decisions or apply reinforcement learning principles to see how that AI model is going to work. And then to finish the feedback loop, this is basically moving from the experimenter who developed a container, which had an AI model, needed some training. You use the data that was produced by the Power test beds that was cleaned, annotated, came back into the Coliseum infrastructure. Once your data and models have been validated, these containers then get moved out into the real test bed. And we have plenty of experiments that we've successfully done. And I'll share some more slide information on how we sort of realize that and how do we intersect AI, network, and RF and wireless all on the Power test bed. So this is happening today. And I'll add more color and details in slides that I send shortly.
Thanks a lot. Maybe a last one before we move on, Manu.
Sure.
So you mentioned, of course, this issue regarding fragmentation. So how can you perceive the role of academia and platforms to maybe avoid this or reduce this risk of fragmentation?
I mean, as we operate research infrastructures as neutral arbiters, right? So we are free from influence. We're free from influence from industry, some of these alliances. And primarily what we've been trying to do with some initiatives such as the, at the start I talked about OpenAirX Labs, that's primarily what we want to do. So this is a place where we have democratized and brought together under one umbrella in a neutral, academic friendly environment, a common place. And with this, we have the ability to create a benchmark validation system where we implement all of these different specifications that are coming from different forums and allow for what the keyword of today are the two I's: interoperability and integration. So what we see is for all of these specifications and these implementations to fight among themselves, there are industry pressures, and there's the pressure to be first and to have your specification be the global standard. But right now, we're not seeing that. And some of these alliances have built firewalls and have built large-scale barriers to entry. And what does another industry player do when they can't get into one forum is they set up their own. We are seeing some more partnerships evolve and come together, specifically between the ORAN Alliance, Open Networking Foundation, and 3GPP, and some other key instantiation players of open source stacks like Open Air Interface, as well as Telecom Infra Project. So these conversations are all happening in the background, but we see academic test beds, and they see academic test beds and academic venues as neutral, zero-threat models where some of these instantiations and implementations can actually happen. And that's the value proposition that we talk to them about, and seems to be making a little bit of movement in that direction. But again, there are plenty of other forces and headwinds that we encounter there, but we're just trying to keep our head down and again, be free from influence, be a neutral arbiter, and at the end of the day, build specifications and build validation systems that can be used by any third party. And that's where we see the value proposition today.
Yeah, we're on the same boat, so let's sail together.
Yeah.
As you said, the winds are quite difficult to manage, but this is also what is exciting. Thanks, Manu. Thanks for joining us for this journey. It gives us an interesting perspective about how things are moving forward in the US. And of course, we stay tuned. Thanks a lot.
Thanks a lot. Thanks for having me.
And now we're going to move on with Bernard. We're going to call Bernard Barani on stage. We are really very pleased to have Bernard with us. It's important that Bernard is saving some of his precious time to listen to those initiatives. And we have been, of course, discussing with Bernard and the Commission since very long, but it's always very important to be well connected. So Bernard, thanks a lot. So Bernard joined actually he started as a communication engineer in industry in the European Space Agency on advanced SATCOM programs. And then he joined the European Commission in 1994. And he is currently deputy head of unit for future connectivity systems, where he leads the definition and implementation of the 5G public-private partnership launched in 2013 and the preparation of the upcoming 6G partnership. So again, many of you knows Bernard and know how Bernard is important in the development of the European roadmap, dealing with 5G, beyond 5G, and now 6G. So thanks a lot, really, Bernard, highly appreciated.
Super. Can you hear me, Serge?
Yeah, very well. Actually, everything is fine. You can move into presenter mode if you want.
And you can see my slides as well. Is
And
it okay now?
Yeah, full screen, and we see you as well.
Okay, I am in full screen mode now. You should see the slides. It's okay?
Yeah, see the slides and you.
Super. So Serge, many thanks for the kind introduction. And actually on my side, I feel very humble to be part of such a distinguished audience and a very high reputation researcher. So I'm just a simple bureaucrat here, and we are trying to do our best to understand where all the various forces are heading to in this complex field, which is telecommunications, which is becoming ever more complex because so many different interests are now joining into this field that used to be a little bit simpler before. Now, to give you just a very short introduction, I belong in the European Commission to the so-called Future Connectivity Systems unit. And in this unit, we have two roles, basically. One role, which is to support industry and to support research and development in Europe in this particular field of telecommunications. And for the next period of time, to 2013 to 2020, we have launched the so-called 5G PPP, which was a set of activities to, let's say, develop industrial and scientific capabilities on 5G in Europe. And the second activity is more on the regulatory side, which is to try to put in place in Europe the framework conditions to have a smooth deployment of 5G, where unfortunately we are not as advanced as the leading regions like US or Asia, but we have good hopes to catch up in the next few months and years. So now our research and development, let's say, leg is moving into 6G or what comes beyond 5G, because now we are reaching the end of an era in that domain. But just before moving into the future, just to recap what we have been doing under the 5G PPP in terms of experimental platforms, we have stimulated experiments, but not necessarily in the sense of this community. We have primarily tried to make two communities come together, which is the communication community and the verticals community, meaning the automotive, the factory people, the environmental people, and so on, and the healthcare people. And to do that, we have supported, at the moment when technology were becoming a little bit stable in 3GPP, the deployment of a large-scale pan-European infrastructure, which is born by the three projects you see on the right-hand side of this slide, Vini, Eve, and Genesis, which are all driven by operators. So it's not necessarily the kind of constituencies you like to see in your, let's say, research test beds and experimental platforms. But Vini comes from Telenor with a very strong BT backup. Eve comes from Telecom Italia with a very strong Orange partnership. And Genesis is OTE / Deutsche Telekom lead. And this all brings together equipments and 5G technologies, which goes up, I think today they go up to release 16. They have implementation of release 16 capabilities. But if you are a vertical, you can come to this platform and test your factory application or your automotive applications. So that's the kind of thing we have stimulated so far. And we expect that this kind of model we will try to replicate in the future, but maybe taking into account different type of requirements. So now, as was said in this event, we are all moving towards beyond 5G or towards further 6G. What's interesting to see is that there is really a global context around this beyond 5G, 6G thematic. So when we look at what various regions are doing, we can see the US, Japan, Korea, China, and in Europe is a different scene, but all these regions are moving very fast into having their own development programs. In Europe, we had the so-called 6G flagship launched in last year, February 2019, by the Finns, by University of Oulu. And on the European scale, we are trying to put in place what we call a smart networks and service partnership, but that's a developing initiative which is not yet completely settled, and I will say a few words on that. But what is interesting to look at is that I think it was already said by the previous speaker, is that there is now possibly much more geopolitical type of considerations running into entering into these overall discussions, which potentially makes the overall discussion a little bit more complex because we can see that different regions, they have kind of specific industrial interest at stake and specific consideration in terms of objectives that do not necessarily match the objectives of the other regions. So to prepare for this future, because we are all aware that every 10 years a new generation comes in, so we already started to think 2 years ago about what could be 6G, what could be a kind of orientation towards 6G, and here we have to be very careful, but because we have seen with the 5G experience that we started with some ideas in 2012, 2013, and then we came with different ideas in 2015, 2016. I mean, originally the 5G story was very much on EMBB, very large capacity, high rate type of access. That was really the focus. No one really talked about verticals. I mean, the vertical story came in the middle of the Ford at some stage, and then everyone jumped into it. So maybe some kind of difference of steering will also emerge in the 6G dimension. I don't know. But we have tried to identify a couple of orientations for the work that we want to stimulate in Europe in the next few years. So on the top right of this slide, what you look at is the so-called vertical use cases beyond 5G. We have seen that 5G has initiated the move towards very deep integration of the communication infrastructures into the business case of specific verticals because of some characteristics which were not present before with 4G. And we believe that this trend will continue and get expanded with potential requirements that will go beyond the 5G capabilities in terms of speed, in terms of sub-millisecond latency, maybe beyond the 5.9 reliability figures. We will have to work out maybe 9 times 9 reliability figures. We see this type of requirements emerging in factories environments, for instance. So this is one thing which goes, if you want, in the direction of more of the same. Now, in terms of application, we see also potentially coming new breed of applications which are not necessarily fully covered or well covered by 5G. Many people are talking about holographic communications. That is very super immersive type of communications. Some people are talking about the Internet of Things. These are all very exploratory concepts. We don't even know if there is a clear business case behind this, but we believe this is interesting to look into this. This Internet of Things comes from the fact that with terahertz type of communications, you can have at the same time a system which is transmitting information, but also sensing the environment, like a meteorological radar on board of an aircraft, for instance. So there are a number of directions which are also, let's say, stimulated by what was mentioned before. For instance, this fact that everything will become machine communication. Some prospects talk about 500 billion machines connected in the next 10 years. So it's really a huge amount of, massive amount of machines to be connected, which will also impose a very strong requirements at the edge, at the periphery of the network, in terms of how the traffic is managed, how the information is managed, which will potentially have impacts on how the architecture is kind of designed. At the bottom of this chart, we talk about societal focus, and this is something we believe is very much important for the 6G discussions. It's about, first of all, what we call ultra low energy type of networks, and this is really a direction we want to promote. We can imagine that because there will be much more computing in networks, there will be much more, let's say, demand to kind of optimize communication and computing energy. Today, most of the energy is consumed in the transmission. I think it's 70 to 80% of the energy gets into the transmission, the radio link. Whereas in the future, this may change, and probably there will be a need to have a much more fine-grained optimization between the energy consumptions on the compute and on the transmit. EMF is also, I mean, radiation hazards or radiation potential dangers of radio emission is something which is becoming very sensitive issue. So we can see some technologies that we could potentially develop to alleviate exposure of the public. And on the right-hand side, all the sustainable development goals that were mentioned before have ubiquitous access, openness, open architecture, infrastructure access, and so on, are orientations that we want to develop in our program. With in the middle, this big brick, which is done, or which is focused on autonomous management of what is called zero-touch management, introduction of artificial intelligence or machine learning technologies to fully automatize the network and provide also ultra-high security with quantum technologies or blockchain technologies, as was mentioned also by the previous speaker. So these are kind of the major direction we can see at this moment in time to drive a 6G agenda, which is developing. So we have some companies which have already established what could be example KPIs. These example KPIs are not fully absorbed or adopted by the industry at large. As you may know, the ITU has the intention to produce a so-called vision paper on IMT 2030. I think their timeline is to have this type of paper early 2023. So between now and 2023, they will collect requirements from technological orientations and then potential visions to kind of deliver the equivalent document than the recommendation M2083 from ITU, where the famous 5G triangle was designed. So here I will not go into the details of the KPIs, but it gives a kind of idea of what could be targeted in the future. Now, when we look at the testbed dimensions, we see, or we have identified on our side, but again, all this is developing work, and we have to refine this with the correct and the right stakeholders. The testbed things that we believe will need very strong, let's say, developments will be on the radio side. Test beds that can validate the usability of terahertz communications over a significant range. I mean, because it's very difficult to have a kind of more than a couple of meters range with this technology. AI-assisted physical layer is something which seems to be also on the radio side becoming an interesting topic, but all the things which are related to spectrum sharing and implementation of cell-free networks, we believe are interesting concepts to bring into test beds. Reconfigurable intelligent surfaces are technologies that we see very interesting to combat exposure to EMF and to really optimize the deployment of the right radio radiation exactly at the right place. Full duplex, potentially AI-assisted, more towards a terminal. I mean, full duplex is implemented in the backhaul today, but it's more difficult to implement it from the perspective of multi-users. So that AI could provide some ideas on how to solve that problem. We see more and more 3D networks. Today, planning is on 2D, now 3D with drones, with satellites. So that will be potentially driving specs and requirements. And as I said, the densification, the compute radio energy optimization is something that will be interesting to demonstrate in testbeds in our view. So on networks, maybe a part of it could have been put in the radio as well, because it has to do with the Open RAN stuff, which was discussed before. We don't know what Open RAN is going to deliver in terms of technology. It will be a big success, but what is pretty sure is that the principles behind Open RAN, open architecture, will certainly be strong drivers behind the 6G or towards 6G evolution. What needs to be done is really to solve the issues which are, in our view, unsolved. I mean, open architecture, Open RAN today is probably not very efficient in terms of energy efficiency, performances. Still, we see the telecom infrastructure projects says that deployment at scale will be validated or available in 2025. So, and also security has potential problems when you open the interface and multiply the threat surface. So yes, the concept is very nice, but probably this is something that lends itself to far more research and validation issues. And then all what has to do with what Serge mentioned in this opening, the fact that the network will become a real computer with this notion of extreme cloud edge convergence towards a huge distributed computing fabric, covering core, RAN, device, and seamless integration. This is something that we can see as a real long-term target to be implemented and simulated or emulated in the test beds. I think I'm not running out of time, so I will go a little bit faster. What is also very important in our view, from a testbed perspective, is really to involve the verticals and the specific use cases of the verticals, because what we have seen with 5G is that really different verticals impose very different type of requirements on top of the networks. And every time, I would not say that you have to make a tailor-made deployment, even though 5G is supposed to be adaptive enough to adapt to the use cases. But this is something that we gain a lot of knowledge by discussing with the automotive people, the factory people, which most of the time they don't understand the same thing as we do, and they don't have the same language. So very important to give these people, to keep these people into the loop. So at this moment in time, to cover this program that we are designing, we have launched 8 6G exploratory projects plus 1 flagship called ExaX. And you can find the list of these projects description on the URL, which is on top. But we are also preparing the so-called industry 6G partnership proposal called Smart Networks and Services. And you can find the roadmap of this partnership at the URL, which is mentioned in the blue box. And as you can see, there are quite a number of industry or academic associations which are supporting this, partnership and its implementation. But we are still in the definition phase, in the sense that we have now made a proposal to the European Council for an overall budget of 900 million euros until 2027. This needs to be agreed by the Council, and we hope that the Council approval will come sometimes summer 2021, which means that we will not be, or just after summer 2021, which means that we will not be in a position to launch calls before end of this year. So implementation of projects first half of next year. So that's our most optimistic time plan at this moment in time. So if you want to get more information about our activities, the 5G trials verticals in phase 3 of the 5G VPP is interesting. You will find some projects that we have launched with a millisecond or 5 millisecond latency. This was a question before. So we have tested with some verticals in the safety, public safety, public security domain, the order of 5 milliseconds latency. The network of the roadmap of the partnership that we propose, you can find it under the second URL, and also information of the specific partnership that we want to launch, Smart Network and Services. also on the 16th March, we will have a dedicated 6G seminar on core technologies from the set of projects that we have launched, which will be announced soon under this URL 5gppp.eu event calendar. So if you're interested to know what we do in AI, ML, in reflective surfaces, in future waveforms for terahertz and so on, that will be explained during this seminar, which will be a technological seminar. So this concludes my presentations. I hope I was not too long.
No, you were just perfect, Bernard. Thanks a lot. I know it's always a difficult exercise to try to share that many information to the audience, but I think it was really clear. At least it was clear in the presentation. Now the way forward is always a little bit hectic, as you know. There was a question from Peter about the KPIs. So you showed the KPIs which somehow reflects an evolution from 5G to 6G, but is it the main driver, or is it something that has been agreed upon the different stakeholders? You seem to be a little...
No, it has not been agreed between the various set of stakeholders. As you know, today there are various 6G vision papers which are being engineered by all sorts of bodies. I think the NGMN is working on its own vision paper. ITU is announcing a vision paper early 2023. There are vision papers by independent companies. I mean, InterDigital that you mentioned before, they have their own vision paper. Samsung, they have their own ones as well. So there are all sorts of papers around, and what we have tried to do is a kind of collection of the various let's say KPIs that you get from these various type of initiatives. But on our side, Arturo Ascora, who will chair one of the sessions tomorrow, is chairing a group of European funded projects on 6G, which plans to deliver their own vision paper in June. And they are working on this KPI set at this moment in time, but there is nothing agreed. But what we can see is that the type of KPIs that we are mentioning here, they come primarily from the vertical use cases that we have studied. For instance, in factories, it's very clear from several German companies in particular being involved in Industry 4.0 type of application. They say, well, when you talk about reliability 5.9, so 99.999% of the time, it's not enough for piloting a robot line. So we need more. So they put forward this type of requirements. The same for the jitter, for instance. In 5G, we don't have any specification for the jitter. Here, they produce this type of jitter KPI because when you want to have a set of synchronized robots working, a large set of synchronized robots that are working on an assembly line, you really need a very precise synchronization of all the robots, and that is kind of the jitter has an impact on how precise they can be in their collective or collaborative way of working. The multiplication by 10 of the capacity is something that we see coming from very specific applications, which again, as I said, we don't know if they will materialize. What we kind of understand is that very intensive, immersive environments, such as digital twins, for instance, they will impose transmission capacity or transmission capacities that will go beyond the 5G capabilities, capabilities today. Because if you want to kind of sample a surface or a volume with a very fine-grained accuracy, you need really a lot of data, and even with high compression ratio, you still need more or much more than the 100 megabit per second per user than 5G is promising. Same for hologram communications or Internet of Sense. But here again, the Internet of Sense notion, we see this as something interesting. This idea of combining the terahertz capabilities communication on the one hand and the sensing on the other hand, trying to develop applications around it. We see this as a very interesting notion. But no one knows at this moment in time if there is a real business case behind this. So maybe some people will come and say, well, with cameras or video cameras, you can do much better. So forget about your terahertz radar. It doesn't make any sense. So there is still a lot of speculation around all this. What we see as a different situation compared to 5G, and this is good because it makes the research world a little bit more open. When we started 5G, very quickly, we had commercial positioning of some operators in the US and in Asia. And this was kind of distorting the research picture. I am not convinced at all that and this is only a personal view, not a commission position at all, but I'm not convinced at all that the NR standard, which has been delivered by 3GPP, is the most innovative standard or the most excellent in terms of scientific capabilities that you could deliver. But it has been done because there was a commercial pressure to deliver something quickly, and then the standardization had to move fast. We are not in 6G in this type of environment, I would say. That, at least that's my perception. We don't see clearly now let's say, commercial ventures mounting around a new notion of 6G with a precise set of use cases, precise set of applications. So it makes the environment a little bit more open and probably a little bit more full of opportunity for the research people like you that you are. And we will be very, very happy to finance you and to support you if we can do something nice together.
Thanks. Actually, this triggers many questions. So one from your part is actually curious about the application focus. If the internet has shown anything, then it is that unknown application and uses will always emerge. So I understand that guiding verticals will be important, but how do you ensure not to meet the real need? It's somehow related to what you just said.
Well, you are fully right, but I don't see that there is an opposition behind the two things. I mean, driving the verticals, let's say, trying to support the agenda of some vertical industries or expanding the vertical universe by bringing more capabilities into the potential applications in the automotive domain or in the factory domain is not contradictory with the fact that you can have a platform which is an open innovation platform on top of which companies can come and implement their own innovations. And for instance, you could have use cases of vertical industries which are implemented on open run or open type of architectures and still keep a lot of innovation capable at the level of how you exploit the data which are coming out of the run through your open interfaces and how you use precisely machine learning to control your run better or to control your interference scenario much better. So I don't think that there is a very strong opposition between the two things. And personally, I like very much the quote of Tom Wheeler. You know, Tom Wheeler, he was the former chairman of the FCC when the Obama administration was still there. And at a dinner in Washington, he made a statement which I find very nice. He said, well, I don't really know what 5G is going to be about. I don't have really a clue of what it's going to be about. But what I'm sure of is that if we give the power to the people with more speed, more whatever, they will invent the usages. And actually, that's what happened with 4G. When 4G was designed, no one had in mind the apps economy, the Uber, the Twitter, all these type of small apps that developed later. I mean, this was not integrated at all in the 4G standardization type of work. People were saying, okay, we just want to give faster access to the internet, which was the application considered in those days. But it was not contradictory with the fact that at some stage, a whole new innovation universe could appear that absolutely no one has thought of. But which is enabled by the fact that you keep a certain level of openness on top of the platform that you are working on.
Yeah, actually, Jörg is exchanging with you on the platform. But let's move to another question. from Andrea about, again, the 6G KPI. So he said that they seem to address mostly the radio part, while the most radical innovation might emerge from novel networking paradigms brought by decentralization of functionalities at the edge. So the point is, maybe there is a much stronger focus on the radio access, while a lot of innovation might come from the distributed nature of the infrastructure.
No, I can only fully agree on that. It's these KPIs were just presented just to make a comparison between what people have in mind today on the radio side and what was presented by ITU some 7 years ago or something like that for the 5G recommendation M2083, which was the kind of key document which was driving research in this domain, or which was driving developments in this domain. But it's very clear that slicing, the service-based architecture, the cloud-native implementations in 5G are things which are much more innovative, potentially, which have much more innovation potential compared to the pure radio type of stuff. These were just illustrative KPIs, but I fully agree that we will have in the 6G domain a lot of innovation that will come from the software implementation of the networks that you mentioned, Serge, in your introduction, the predominant role of software. This is something that we fully agree to, and we are fully supportive. The big problem we have, and this is something I will share with you openly, we have a problem in Europe because we don't have the players. I mean, this is right. When you talk about Open RAN, I mean, the concept is nice, but who are the key players on Open RAN today? It's US and Japan. I mean, Europe is not moving very fast in that domain. I mean, operators are very much, they are adamant to get the technology. They want the technology. I mean, there are all sorts of operators, green paper, white paper, coalition paper, which is calling us, the public people, the public sector people, to put in place a framework support to support this type of things. We are prepared to do it insofar as there is a public interest to do that. But what we would like to do, and this is a European problem, and that we can unfortunately not bring to the other regions, but what we would like to do is if this Open RAN story takes up and that there is really a software innovation ecosystem that emerges out of disaggregated type of networks and cloudified type of networks, we would like Europe to have a very predominant role in this picture. And at this moment in time, our question is, how do we make it happen? So if you have good ideas, Serge, share with us.
I have plenty of questions as well on that for you. But let's maybe take the last one, because you mentioned Arturo. Arturo is with us. And he's asking the relationship you envision between the SNS partnership and research infrastructures. Actually, in many domains, there is a very smooth liaison between the research questions and the infrastructure that you need to basically provide evidence. So, what are your thoughts about this?
It's a good question, and actually, I will make a very simple answer. I'm not in a position to really answer that one, and I would prefer Arturo, who is kind of horse riding between the two environments, to give us some ideas on how to make this happen. Because we have a very difficult situation in the Commission. I mean, it's not a very difficult situation, but we have to make some choices. And I know, Serge, that the research stakeholders that you are representing, sometimes they are not happy with us because you have the impression that we favor too much the big industries, the industry actors, and we kind of kill the innovation because we don't give room enough to the academics or to the innovator community to contribute in our program. And that's an equation we have tried to solve for quite some time now. And I must say we have not yet found a way to sort it out. So if that means to have a strong industrial impact and at the same time to have a strong innovation capability from the academics, from the research community, from these people. I'm sorry for the people who are not from Europe in this discussion, because this is really European type of discussions. But whoever has good ideas on how to reconcile these two worlds in such a way that it brings, let's say, our region in a very good position will be very much welcome.
No, but Bernard, we understand the tussle, and we understand how complex it is to define the roadmap with respect to the public funding or public-private partnership. So no worries about this. But of course, this is why, again, it's nice to have even a small session here with Japan and the US. And actually, maybe the last question, because otherwise we'll be behind schedule, is I was listening to the development regarding the international cooperation of the Commission for Horizon 2020. And I was just questioning myself about how do you see the international cooperation yourself regarding, again, maybe 6G, to take something which is on a much longer perspective?
On international cooperation, we have not yet made up our mind exactly on how to proceed on that. What is sure is that we will not proceed the same way as we did in Horizon 2020. That means have a kind of high-level agreement signed between the European Commission, the commissioner, and a minister in Japan or a minister in Korea, which sets the scene of some targeted joint research between Japan and Europe, or between Korea and Europe. This model, this top-down model, we will probably not use. We will use more a bottom-up model, which will be left more to the discretion, or to the bottom-up that will be left to the choice or to the selection of the actors. So we still have the possibility that whatever project we finance includes international cooperation and international cooperation actors. I don't think, though, that we will go into this machinery of joint goals, joint projects, because it's very, very complicated to implement. And at the political level, they don't see the interest, to be quite honest with you. They don't see the outcome. They don't see what comes out of it. And now we have a dialogue which has been established by our administration with MIC in Japan, with MSIT in Korea, with IMT 2030 in China, and also in the US. And we are trying to understand what we could do together, but so far it's again one of our question marks here.
Okay, thanks a lot, Bernard. Really highly appreciate it. It's really good to have you with us. It doesn't happen often, so we'll certainly invite you again. Well, seriously speaking, really appreciate it. It's good to see the development of this SNS, which is still open, but we are going to take a very close look at it. And we will ask Arturo to help us, of course.
Voilà. Great pleasure on my side. And
thanks a lot, and take good care of you.
Thanks a lot.
We're going to hand over to David now. So thanks, David, for joining us. I see that you are properly connected through 4G.
This is correct. Can you hear me correctly? I am sorry. I had a breakdown of the wired network in my village. Like many of you, I am at home. I am not in my office in Paris. Nevertheless, it is really a genuine pleasure to be attending to this event today. We had a few exchanges earlier with Serge and other French stakeholders in this. And it is really an honor for me and a privilege to have the occasion for a few words among all of you. I am speaking today from the French Research and Higher Education Ministry. So very humbly, just like Bernard said earlier, even worse, probably. I will try to keep short. I decided not to make any slides to be shorter. But it is a very important opportunity for us. Me and my colleague Akima Shaoshi, you probably most of you must know. Yes, this is the opportunity for us to deliver to the SLICE's European community a few, let's say, major encouragements messages for your science and technology activities. Obviously, digital society, we discussed a lot earlier today, and digital transformation, by all means, in all industries, require fast, very efficient scientific advances in digital sciences. And this will be probably possible only if we offer you, our digital science researchers, an efficient and up-to-date distributed digital research infrastructure with a complete set of equipment, tools, storage, processing, communication technology, and probably more than you know, and I don't. There's future internet technologies, including 5G, 5G plus, 6G, we discussed a lot, IoT, and so on, distributed systems, really appears to us as a key strategic asset. Our colleague John Croft from Cambridge, UK, explained this very nicely a few minutes ago, more than a few minutes now, mentioning various necessities such as service performance, resource frugality, among which energy efficiency, but also resilience, security, and modularity, etc., etc. All this to offer a wide range of digital services. We are talking about verticals. We talked earlier with Bernard. And of course, very particularly in this very peculiar context we are all into right now with the COVID scenario, we will not emphasize too much about that. But this is obviously something happening also in the digital world. We are aware of and would very like to emphasize on the fact and the importance of the experimental approach, probably combined with simulation also, with the ability of experimental platforms, as we said, such as SLICEs at the European level. And at the French level, we have a platform, Serge is very aware of, which is called SILEX at the French level. You probably certainly know about this French research infrastructure, which was labeled in 2018 in France, and is probably a very significant contribution to SLICEs as far as I understand. And we hope to, let's say, to pursue this support of the French government in SILEX in a way or another. We would like also to underline the need for European partnerships, obviously, very necessary for the digital sovereignty. This was quoted, underlined by previous speakers, such as Manu Gozin from Boston, Massachusetts. This doesn't prevent at all from international collaborations toward excellence, like with our fellow partners in Japan and in the US and other countries outside Europe, obviously. It is also important to emphasize how necessary it will be to combine, let's say, basic fundamental research and scientific excellence. Let's say very adapted to international discussion, by the way, and it is important to combine this with work on innovation, industrial and societal application, and even contribution into regalian domains at the France or European levels, obviously. So what I can share with you here is that in France, related to the European Economic Recovery Plan, we are working on a strategic agenda for important national strategies. Most of these strategies deal with digital and are somewhat related to the challenges which are addressed here by the SLICE's research infrastructure. To name a few of them, and we already talked a lot about some of them, artificial intelligence. Manu, for instance, largely commented on the interest of IA, RF network convergence. Obviously, something very important also is cybersecurity to be applied here to network and distributed systems. There is also a strategy reflection about obviously future of telecoms technology like 5G, 5G plus 6G, etc. We discussed that. We are also thinking about cloud and green IT. All these investigations are done mostly again at bilateral or European level. Electronic and hardware technologies, microelectronics, for instance, have no sense if not thought at the European level at least. And I have a think also to our Japan and US colleagues at this level. By the way, it was discussed, it is probably a bit more long-term, a bit far-fetched, possibly in some terms. We are having the launch of a very important strategy in quantum technologies in France. But not to mention also more vertical strategies like robotics, very notably for industrial recovery, of course, and also smart cities, digital and earth, precision agriculture, etc., etc. This is why, by all means, the scientific challenges addressed by the SLICE's research infrastructure projects and partnerships are for us of utmost interest, seen from the French Research Ministry again, and therefore have all our support. Thank you very much. I can't hear you right now.
Yes, I apologize. I was muted as usual. I was just saying thanks a lot, David.
Oh, good. I was afraid to have lost you.
No, because I didn't even have the time to introduce yourself, and it's really important because it gives a member state perspective on this kind of initiative. Because for those who are with us, David is the current scientific director at General Direction of Research and Innovation with the French Ministry of Research and Higher Education. And he leads the Department for Mathematics, Physics, Nanoscience, Science and Technologies for Digital. And among others, current national projects under construction deal with cybersecurity, future of telecoms, artificial intelligence, cloud technologies, electronics, and so on and so forth. So that's really, really important. Again, because, not to be friendly, but we are lucky in France that we can have a liaison with the French ministry at this level to promote the importance of this kind of test platforms. It's very obvious in other domains, and actually, David, you are covering a quite broad spectrum of fields. But in computer science at large, it's very difficult to make a convincing point about the fact that this kind of scientific instrument is important and is not covered by production facilities. And it's still very difficult. And we have, of course, a lot of colleagues attending the workshop from different countries. And it's still lagging behind in many countries. It's still very difficult to promote this kind of work and activity. So that's very important for us that actually, as a member state in Europe, you really support this kind of initiative, and we are very grateful for this. Maybe just a few questions, because, as I said, the situation in the different member states is different, as we have seen, of course, that in the US or in Japan, they have different perspective as well. So because of this fragmentation in Europe and because, of course, also of the opportunity provided by the European dimension, this coordination is really, really important, because we believe that we can only compete in the good sense, so being at the front of excellence as well as impact at the European level. But of course, this needs to align the national strategy with the European strategy. And again, one of the main difficulties that we faced in the past was the ability to convince science at large about the fact that we also need research infrastructures. And I'm just curious about how you see the development of research infrastructure, especially in digital, because, for instance, in S3, there were no digital, let's say, category of test platforms until very recently. And actually, there is no test platform in this domain at S3. So you find plenty of them in high energy physics or biology or energy, but none in digital. So how can we better make our job of convincing, let's say, the different stakeholders, because we have here colleagues from different countries, to support the claim?
This is both a very difficult, challenging, and a very interesting question. I am not sure I will answer directly what you are asking for, but my feeling is that what allows people to understand a platform, an experimental platform, is necessary is induced by the fact that everybody should understand that digital, contrarily to what most people believe, is not only in the virtual world. And it is very often forgotten that any digital system, in the end, is based on a physical system. And this is why an experimental approach is absolutely necessary, because of all the, let's say, the uncertainties of the physics world, when you are in the digital world, maybe you can imagine everything can be modelized, let's say, monitored by, let's say, digital twins. But whatever you do, in the end, these digital twins, they run on a real PC with a motherboard, with a lot of imprecision, with energy coming more or less. And I just realized my network is not working as we said earlier. This is just a joke, but it's not a joke. It is because it explains us that all of this is relying on a physical level also, and this is why experiments are absolutely necessary, because a physical level brings a lot of uncertainties. There are also uncertainties at the digital level, obviously, but maybe some people could dream of dealing that without any physical platform. When people realize the digital world is just, let's say, encroached on a physical layer, they realize things have to be tested. You don't fly a plane without testing all the electric appliances and capacities. Obviously, you can't do that on a general network either. I don't know if it gives you any hints of the way we could try and succeed together to convince at all levels that this is necessary if we want it to work, to perform at a good level of resilience and efficiency and safety and security safety. But I'm really profoundly, genuinely convinced of that.
Well, thanks. And the other point is also about the fact, and in France, I know this is the same situation, of this other type of fragmentation between the network and the compute, as well as, the storage and so on. So I know there are a lot of discussion in debate in France about how you might make those things evolve, because as you have seen, maybe if you have followed the presentation earlier, that everything today is perceived as being fully integrated. I mean, you can't look at a network without the cloud-based, development. So what are your thoughts about this with respect to the French agenda?
I don't, well, obviously, let's say the digital technology on the large spectrum are very largely addressed on the French research agenda, as you know. We still have some leaks, at some levels where things have to be explained. You're right. And I don't completely understand your question about the global picture of the general frame, but I think there is, if I understand correctly, there is the necessity of acting both at the highest level of architecture and at the lowest level of distributed system. This is the way I see it, but I don't feel I answer completely your question.
No, but that's fine. This is just to say that for years we looked at digital infrastructure as being, completely separated. I mean, you have, for instance, in France, you have Renater at the research network, and then you have other organizations that are dealing with the compute and so on and so forth. This is something that is very difficult to make evolve. And we have a question from Bernard. What do you think of having license-free zones for spectrum as done in the US so that infra experiments can be easily deployed? Should it be done in Europe? So that's, I don't know whether you can address this one.
Well, I have difficulties with this question. I would like to understand at which to which extent we are talking about. Is it in a lab, in a campus, in a country? Could you possibly precise a little bit the question if you understand it, Serge?
Yeah, so actually one of the challenge is about spectrum. And as you know, spectrum is very strongly managed and controlled. And if we want to forecast or plan some new experiments dealing with spectrum management, we need to have access to this spectrum. And there are tons of initiatives, for instance, in the UK, or as mentioned by Bernard, in the US, to release part of the spectrum for providing opportunities for experimentation. So I know, Bernard, that this is under the control of the French FCC called ARCEP. And so far, they have released some spectrum for experimentation. So for instance, one part has been released mostly to Nokia in the close suburb of Paris. And some other parts have been released elsewhere. But it's very, very structured and organized. So it's I don't see it as being very easy to access, but it's certainly a very important point, because that's something also that we are pushing ourselves, so that we could also benefit from this kind of spectrum to play with. But that's something that is a little bit out of scope of what David is basically organizing.
Yes, I take the point. I am not allowed or in position to answer this one. I'm sorry about that, Bernard, but I take the point. I couldn't realize how important it could be, and I also have the feeling that it's not so easy to release these spectrum, which is why I asked the question to which extent on which size. Area size, it is relevant to do these tests. I am aware that a test can be done in, let's say, academic facilities, but probably it's not enough at all for what you want to do at the system and distributed system level. And I am wondering if it is possible to do it at, let's say, a campus level or more or less, which probably is easy to release. If you want to do it at the town level or city level, it might be a little bit more complicated and giving some real serious issues.
Yeah, again, thanks a lot. I think it was very, very important to have the testimony and the positive one, of course, from a member state, mostly dealing with research and innovation. Again, what is important is that what is on the roadmap of SLICES, as you know, is really to try to orchestrate the involvement of member states so that we can have a European perspective, because otherwise it's simply impossible to get the level of resources and human resources and capacity to do something at the level of what our colleagues and friends in the US or in Japan are doing. Thanks a lot. It was good to have the US, Europe, and the member state like France. And thanks a lot also for your continuous support over years. Thanks, David. And see, it's amazing. It's 5:14, so we are 30 seconds ahead of time. Just for Peter to take the lead now for concluding this first afternoon. Again, we know that moving into virtual is a little bit, tiring in the sense that we cannot sustain a full day listening to a screen. So thanks to everyone. And Peter, you have the responsibility to handle the closing of the first day.
Yeah, okay. Thanks a lot, Serge. And indeed, well, I prepared a few slides. I hope you can see the slides and hear me well.
Yeah, perfect. Everything is good.
Okay, good. So in fact, I think if you just make a roundup of first day, I think it's clear that we're going to a very digital society with everything connected, always connected, everybody connected. And I heard a very nice terminology on this, democratized. Very difficult to pronounce, but I think it's indeed what we should aim for, is getting everybody connected and also make it easy for everybody to get connected. And we also have seen on the different presentations that the digital society is on the agenda of a lot of different countries on all levels of public authority, if it's local, regional, European level, national level, and also worldwide. Now, it's so that the digital society is supported by a wide range of technology. We have been hearing about, let's say, connected vehicles, but also underwater drones looking for oysters and so on. And the evolution of the technology is going very fast. So we're just introducing now 5G, and we're already moving and working on 6G. And one of the assumptions is that the move from 5G to 6G might be through local private 6G networks, and try to build it bottom up. Now, also from the presentation out of the Commission, there is a clear initiative to go and to stimulate work and research on the 6G. Now, although the future is very difficult to predict, we already know what it will be about. It's clear from all the different presentations that we heard today, it's going to be about smart devices and networks, more autonomous devices. So, in fact, something I learned also today is that we're going to lose the human-centric aspect of the network, because more of the devices are going to connect and interact autonomously without interaction by humans amongst themselves. There will also be more intelligence in the network and in the devices. There will be more flexibility, programmability, automatic updating of networks. And especially one of the things that also came back several times is customized services, really to try to build and to make the service of the network customized to the user. It will, of course, be faster with higher capacity, lower latency. We're looking at reliable networks and connections with secure and private interaction and interchange of data, with lower energy, looking for a sustainable future. But one of the things I'm also a little bit curious about is whether or not, like, for example, with I got a feeling that indeed from 2, 3, 4G, it's a kind of evolution. 5G, there is a kind of break in this trend. There is really a break changer. there, a trend changer. And we might also get the same thing if you go from 5G to 6G by introducing quantum technology, but also artificial intelligence. I think this is really something that might be a game changer in the network. Now, it's so that digital society is built on heterogeneity. Out of the presentations, there was a focus on 6G, that's right, but this is only part of the technology for the future network and future internet and the future digital society. New ideas, new concepts, they have to be implemented in a very highly competitive environment and with very rapidly evolving requirements. Consequently, the research, the innovation, development that calls for an up-to-date testing facility with skilled support. And I heard something about experimental twins or digital twins. I would call it experimental twins, really having experimentation facilities that mimic completely and for 100% the real network, so that people can try out their ideas, their concepts on something which is really completely the same as it would be the natural or the normal network. But doing this is far too expensive for many players. So, and there I think that Slice's research infrastructures comes into play. We have the objective to serve the community, to support this transformation towards digital transformation, to digital society, by offering a very low threshold access to top quality and vendor neutral research infrastructures in a broad range and a broad spectrum of activities in the IT domain, and covering this very wide range of technology and supporting this heterogeneity. So, in fact, we would allow with this infrastructure to solve some of the problems that were raised and discussed today by allowing academia, research groups, SMEs, startups, industry to research, develop, test, valorize, benchmark the new concepts, the new technologies and new projects, and also the upscaling of their ideas in a very trustable, reproducible manner, and also in a vendor-neutral environment. So many scientific challenges still lie ahead, with a very huge socio-economical and industrial impact, and within an international and a worldwide context. And we heard several times also the geopolitics being mentioned. And these are in fact the three topics which are covered tomorrow in the second part of this workshop. So join us online tomorrow morning at 9 a.m. Brussels time or Paris time, Central European time. So thanks. I'm handing over to Serge again for concluding remarks.
Thanks a lot, Peter. No, I have nothing to conclude in addition to everything you said. So please join us tomorrow. We are going to start at 9 a.m. So you have registered, so you already have the link for joining us. There will be a first session, as mentioned by Peter, dealing with scientific challenges, and a second one with socio-industrial perspective, and then a last one, which is really, really important as well, because it deals with infra-EOS industry as potential catalyst for slices, which is not only European, I think it's really a major challenge for us worldwide. Thanks a lot, right on time, and enjoy your evening after 4 hours of virtual entertainment, and we'll be very pleased to see you again tomorrow 9 a.m. sharp. Have a nice evening. Bye-bye.
Okay, bye. To see you tomorrow.